Hello, hello. Now you can hear us. Can you unmute yourself? Unmute yourself and try to speak from outside.
Hello, am I audible? Hello.
Hello.
Hello, sir. This is Animesh.
Okay, we can hear you.
Okay.
एको क्यों आ रहा है? तो ये भी चल रहा है क्या?
I guess so.
Hello, hello.
No, it's not.
It's not. एको क्यों आ रहा है? क्या म्यूट नहीं है?
But ये म्यूट होगा तो बात कैसे?
Hello.
Okay, at the beginning we are going to use this microphone, and while talking we will use that.
Right.
But that should be checked.
Hello.
Amit or Purbita, are you there?
Can you hear us, Sujata?
Yes, I can hear you. I am having a problem getting in with two of my devices because I will be using it, but is there any option?
Register using a new account.
Yeah, you need to register from the new account and use it to.
But okay, let me try. I have registered with 2 emails, but still I'm not able to. Maybe because it's on my side.
Oh, but it should, because we already registered ourselves from 2 and we are logged in actually. It should work. That's the point I want to say.
Try.
Yeah, better to come forward. Yeah.
Switch on her camera whenever she's ready so that she could see.
Oh, Sujata, can you switch on your camera so that we can see you as well? Yeah, we can see.
I think it's 9:45.
It's already 9:40. Yeah. I'm requesting all of the participants, if possible, please turn on your video so that we can see all of us. Okay. Thank you. Okay. You're the chief guest.
ये ऑन कैसे करना है?
It's on. It's not on? Maybe they can hear you actually.
Hello? Hello? Okay. Yeah, I hope everybody is ready. Yeah, we are really fascinated by the fact that we could put together this event in the hybrid mode. Welcome to ISLA 2022. So we have got a few participants here offline and lot of participants online. I request all the online participants to switch on their cameras if they can, so that they will be captured in the photograph along with all the dignitaries on the dais. So I'm very happy to have, we are very happy to have Professor Shalabh, Dean of Academic Affairs, IIT Kanpur, to inaugurate this event. Our mentor and support from the department, our Professor Mahua Banerjee, the head of the department, who is also speaker of the event. She is also here to grace the occasion. And our speakers who are giving lectures in the offline mode, they are also here, and Professor Sujata Ghosh in the online mode. So I want to welcome all of you, and let's hope that this event will bring more knowledge on the path to learning more logic. Yeah, so logic is not really a a well-studied subject in our country. And this is our attempt to at least start some kind of raise some awareness about this subject in the country, so that more and more people will get involved in the subject and learn. So we are very thankful to two professors from abroad, Professor Nick Bezanishvili and Professor Marcus Tressel. So they have agreed to teach in this school. This school will have two different streams, but we hope that you will be benefited from both of them. We have tried to keep them elementary in the beginning, and then towards the end, it will be more advanced. So please stick around and try to learn as much as possible. I would like to request Professor Mahua Banerjee to say a few words.
Yeah, thanks, Amit. I'm really so glad that this event is taking place here with all the efforts that have been put in by Amit, Purbita, and the rest of the organizing team. And I'm thankful to all the speakers who have agreed to speak, be part of this school. So I must add here that to what Amit was saying, that that we hope that the school will sort of increase the knowledge, increase the awareness, and increase the enthusiasm towards this very, very fundamental subject of mathematical logic. I must add here that IIT Kanpur Department of Mathematics and Statistics is one of the very few, I'm not sure if it's the only one, of the mathematics departments which has a compulsory course on logic. And now it's been running for about 20 years. So, so this is a really happy occasion that the department, with whatever minimal support it could give, and with the support of the Dean of Academic Affairs, Dean of Student Affairs, and the Institute, is able to host it with the efforts of the team. So I wish the school all success.
So now I request Professor Shalabh to say a few words.
Dear friends, colleagues, and my distinguished speakers and very distinguished participants. On behalf of the IIT Kanpur, I would like to welcome to this workshop, which is being organized on behalf of the Association of Logic in India, that is ISLA 2022. And yeah, I'm really grateful to my department colleague, Dr. Amit Kumair and Dr. Purbita, that they have taken this initiative to conduct this workshop in this hybrid mode. And I'm sure that this mathematical logic is such a fundamental subject, but it is not really taught in many universities. And IIT Kanpur's Department of Mathematics and Statistics is one of the department which is taking this course to be very seriously. And in the given perspective, it is very important that the knowledge about the mathematical logic is required to be spread around the world among the students, so that many more applications can be developed based on this. So in this direction, I really appreciate the efforts of our organizers who have taken the pain to organize such a workshop. And I'm grateful to all the participants who are going to spend their time in this workshop. I'm really grateful to all the speakers around the world, from University of Amsterdam, University of Manchester, ISI Chennai, ISR Pune, IIT Guwahati, and my own institute, IIT Kanpur. I'm really grateful to them that they have taken time to speak in this workshop and to educate our participant. So I really wish you all the best, and I wish that this workshop gives a new dimension to the learning of mathematical logic. Thank you very much. And if to all the participants, if you have any issue in having a comfortable stay or comfortable learning in this workshop, please let us know. We will try our best to sort it out, and we will be very happy if you go back after a couple of days by learning the topic of mathematical logic. Thank you very much.
I want to bring out a couple of specialities of this. Yeah, as we have participants from all over the world, we have got registered participants from South Africa, Germany, and USA and UK as well. And I also want to highlight one major thing, that in this school, we are giving chance to 2 students who are sitting on the dais, who will be giving lectures on basic category theory. They have just finished their degrees, BSMS and BTech in electrical engineering. Yeah, but they are experts in the subject. So I hope that all of you will support them. They are teaching for the first time in their life, yeah, in front of such a large audience. So we hope to have support. Now I invite my co-organizer, partner in crime, Dr. Purbita Jana, to give a vote of thanks.
So, thank you so much for coming here. I'm really grateful to Professor Shalabh for to accept our invitation to be the chief guest of this event. I'm really thankful to Professor Mohua Banerjee, our head of the Department of Mathematics and Statistics. And also I'm thankful to all of the speakers of this event. And I hope that that school will run very well and you will learn something out of that. Thank you so much. So from 10 o'clock, we are going to start our sessions and it will be started by the lecture of Professor Sujata Ghosh on order and lattices. So after 5 minutes, we are going to start with the main program. Thank you so much. Thank you. Yes, please. Thank you. Thank you so much. Hello. Hello, Sujata, can you hear me?
Yes, I can hear you. There must be some problem. I don't know. I'm not able to log in through my other device. I wanted to do it with 2 devices, but anyway.
So do we need to like
No.
share or something like that?
No, the whole point was I wanted to write on the slides as well. That won't be possible now.
I see.
Oh. Yeah. Anyway, let me see. Maybe today, now I will manage somehow. Maybe before tomorrow, we can sit together and see how to solve this problem.
Okay. Okay.
Maybe whatever I plan to do on writing, I will do it tomorrow. And maybe discuss the proofs today. So, and whatever we are facing now, we can discuss this evening so that we can sort it out.
Okay. Okay. Okay.
I don't see any other way.
Yeah. Okay. So, Anna, could you please make her the co-host so that she can share? So, could you please try to share your screen?
Yeah.
Using the same name?
No, different. There is some problem with the devices. Yeah, it's visible.
Can you see just the slides or something more as well?
Just the slide. Yeah, just the slide. No, I can see the side view as well.
Yeah, that's what I'm asking. You can see the side view as well.
Yeah.
So now it's okay, isn't it?
Yeah, now just the slides. Yeah. What's the time now? 2 minutes is it or 1 minute? Hey, it's 10 o'clock or it's like, oh. Okay. Today we are going to start our school by the lecture of Professor Sujata Ghosh. She is from ISI Chennai, and she is going to deliver her lecture on law orders and lattices, which is the very preliminary things to study, to go through all the lectures. Okay. So I hope that you will enjoy the course, and there will be a tutorial on that at the end of the day. And I wish to thanks Professor Sujata Ghosh to admit this invitation to deliver this lecture in this school. So Sujata Di, please continue. The stage is all over.
Okay, thank you, Purbita. So, good morning, all of you. Can you hear me properly?
Yes, we can.
Okay, fine. Thank you. So today is the first day of the school, and this is the first lecture. So I will be, as it says on the slide, I will be talking about orders and lattices. And so this talk is kind of to set the stage for the experts who will deal with more advanced topics on dualities and logic, as well as other stuffs. And let's see how it goes. So before starting, I will like to thank Amit and Purbita for giving me this opportunity to speak before you. And of course, I would like to thank IIT Kanpur for agreeing to host this event. And this is very nostalgic for me personally, because the last ISLA that was held in IIT Kanpur was in 2008. And I had some very wonderful memories of that ISLA. So having ISLA at IIT Kanpur once again, it's really nice for me. I really wanted to go there, but because of certain reasons, I'm not able to be there physically. But anyway, so I can be there virtually. Okay. So let's see, what is order all about? The one thing that we can say about order is order is everywhere. But before going into that, let us talk about the books that we can, that generally deals with orders and lattices. There are various books you can take a look into. There are some classics like the books by Berkhoff, Ratzer, and there are several others as well. The Universal Algebra book by Sankat Panawar and others, that also deals with these orders and lattices. But what I will follow today and tomorrow in both my lectures, I will be following this book, Introduction to Lattices and Order by Davy and Presley. In fact, all the exercises that we will have today are also from that book itself, with some modifications here and there. And the lectures will also go along with some modifications from the book here and there, which I felt necessary. So for this lecture, the book to follow is Davy and Presley. Now, as I just said, order relation is everywhere. You can think of order everywhere. For example, you can think of X is larger than Y, X is tastier than Y, X is faster than Y, X is a subset of Y, X divides Y, X is a part of Y. In all these examples, like taken from real life, or mathematics and some formal areas. So there is kind of a ranking between them, and the order is between two elements, and order is all about this kind of ranking as we understand intuitively. So intuitively, what we have as an order relation is nothing but a relation that ranks elements against one another. So, but without further ado, let's move on to giving some more formal definitions. But before going into even order relation, we would like to ask, what is a relation itself? As we said, order relation is a relation when we attach the word relation to it. But what is a relation? So as we all have an intuitive understanding of relation, and we talking about relation between two objects, and we generally mention them as a binary relation, such relations, and it's nothing but a property which is this kind of describing two objects that are related in a certain way. So, for example, if you consider the less than relation, the divisibility relation, or the friendship relation, these are all examples of relations. So what do we need to do, like to describe a relation? What we have is, we have a set of objects, and there we consider some pairs of objects which are in some kind of a relation. But like between two numbers, we can have the less than relation. Again, between two numbers, we can have the divide relation, or between two persons, we can have the friendship relation. So for the friendship relation, the set of objects is the set of all individuals. Okay. So in that sense, to describe about relation, we need a set of objects, and we talk about relation on that set of objects. So formally speaking, if we consider A to be a non-empty set, which is kind of the set of objects I was just talking about, then a binary relation R on A is nothing but a subset of the Cartesian product of A with itself. That is a set of ordered pairs. A binary relation is just a set of ordered pairs. So for example, if you consider the base set to be n, which is the set of natural numbers, you can think of this less than relation, which is consisting of this ordered pairs 0, 1, 1, 2, 0, 2. All these elements would occur in that less than relation set. And then you can think about the equality relation as well, where all these pairs 0, 0, 1, 1, 2, 2, and so on and so forth will occur. So here are some examples of such binary relations. And now what we just described, order relation, which intuitively provides certain kind of rank, is a particular type of binary relation. So now, before going into the formal definition of the order relation, let's see what kind of properties we would like to have of this order relation. So what kind of properties are natural for this order relation? So something is that, let us say we continue with our n and we consider the order relation, which talks about x is less than or equal to y. Okay, this relation. I'm not saying like it's kind of a ranking relation that we have intuitively, and we have studied this from our childhood. So now, of course, if 100 is less equal to 200 and 200 is less equal to 1000, that would imply that 100 is less equal to 1000. So if we abstract out of this idea and think of any set A, we can think of that if for all x, y, and z, if x is less equal to y and y is less equal to z, then x is less equal to z. In fact, it is actually, as I just mentioned, it actually holds in n as well. So this property that if for all x, y, z, if x is less equal to y and y is less equal to z, then x is less equal to z. We call this property to be transitive. And once again, another in properties, of course, one is if you can less equal to is less than or equal to. So of course, 1 is less equal to 1, 99 is less equal to 99, and so on and so forth. And we get this kind of a property as well, that for all x, x is less equal to x. So such a property, we call that property reflexive property. Okay. So what kind of another property that we can think of, or are there any other properties that we can think of? So now consider this property, that 21 is less equal to 47, but of course, 47 is not less than 21. Also, 30, whereas if you consider 34 is less equal to 34, or let's say 21 is less equal to 21, as well as on the other side also, you can think of 21 is less equal to 21. So on both sides, when it's the same number, you can, like it automatically, you can say that 21 is less equal to 21 and 21 is less equal to 21, or similarly for 34 or any other number. So such a property, to get hold of such a property, we consider this antisymmetricness. What is that? That if x is less equal to y and y is less equal to x, that should imply that x equal to y. Or in other words, if you think about what is going on, so what you have is that, take any set B. Suppose if you have some relation R on B, a binary relation R on B, so we have that if x is related to y and x is not equal to y, then y should not be related to x, or the relation is kind of one direction. Okay, so that's what we are talking about here. Okay, before I go any further, so I would love, generally when I discuss, I would love an interactive session. So please don't hesitate. I'm not able to see anybody. So I am not able to see the black boxes as well because of I have to look at my slides when I'm talking. So I would love interaction and questions from you. So, and I'm not able to see the chat or anything. So if you have a question, please unmute your mic and ask me that question. Okay, please don't hesitate. Please don't hesitate. I would love to answer your queries. Anyway, so if you think about this antisymmetry, the idea is that if x is related to y and x is not equal to y, then y should not be related to x. So to get a more idea of this property, let's consider this set of elements with the relation given by the arrows. Okay, where the relation R is given by the arrows. So the whole point is, even though we allow self loops, we only allow one edge between two distinct nodes. Okay, even though we allow self loops, we only allow one edge between two distinct nodes. So that's basically the idea of antisymmetry. So now, given the ideas of reflexivity, transitivity, and antisymmetry, we are all set to define what is meant by a partial order. So what is a partial order? So take any non-empty set A, a binary relation R on A is a partial order if R is reflexive, antisymmetric, and transitive. And what those definitions are, we have just now discussed. So a partial order is a binary relation which has the following properties: reflexivity, antisymmetry, and transitivity. Okay, an order relation is a particular type of as I said, is such a particular type of binary relation which satisfies these conditions. And when R satisfies these conditions, this pair A, R, where R is a partial order of A, we say this to be a partially ordered set or a poset. So it means that we have a base set A and we have some structure on A given by this relation, which is a partial order relation, and such a pair we term them as poset. Okay, so now just a natural question, why are we calling them partial order?
The answer from the audience here in the final.
Sorry?
I'm just asking someone, just a moment.
Yeah.
Because if we consider any two elements of the set A, we are not sure whether those two elements are related to each other.
Exactly. So we are, so let's see. The whole point of partial means, as somebody in the audience just said, that we are not sure whether two elements are related or not. And how can we derive that, this relation? So let's look at some examples of partial order. So let us consider some examples. So now consider this set of all divisors of 12. So 1, 2, 3, 4, 6, and 12. This is the set of all divisors of 12. So now if we consider this kind of pictorial representation, we have these arrows, as we just shown a pictorial representation. We have these arrows signify those orders from bottom to top in general. So 1 divides 2 and 3. Of course, 1 divides everything, but we are not, and 1 divides 1 as itself. If we do not consider the reflexive arrows and the transitive arrows, because they kind of then the readability of these diagrams get kind of lost. So let us not consider the reflexive and transitive arrows for now. And let us consider just the direct relation. So 1 divides 2, 1 divides 3, 2 divides 4, 2 divides 6. Sorry, I have forgotten to add 1 arrow. I should have added 1 arrow. 2 divides 6, and 3 also divides 6, and 4 divides 12, and 6 divides 12. Of course, the transitivity is anyway there. So as you can see, 2 does not divide 3. So if you see, all the conditions of being a partial order is satisfied here, because even though we have not, we consider all the reflexive arrows, all the self loops, we have 1 is less equal to 1, and the divide relation, every x divides itself in this set. So we have the reflexivity, we have transitivity. If x divides y and y divides z, then x divides z. We have transitivity. And we have antisymmetry as well. If x divides y and y divides x, we have x equal to y. But see, 2 doesn't divide 3, or 3 doesn't divide 2. So not all elements are related by this order relation. Some elements we can relate, some elements we cannot compare. So in that sense, this relation is kind of partial over the set of elements. Okay. So here is one example of a partial ordered set. Now let us consider another example. Now here is the subsets of all the sets, subsets of the set A, B. So here is the list of all the subsets: the empty set, the singleton set A, the singleton set B, and the singleton set AB. Now, if you consider the subset relation, then you can see that you have the following representation. So phi is a subset of A, phi is a subset of B, and both A and B are subsets of AB. But neither A is a subset of B nor B is a subset of A. So as you can see that A and B are not related, and of course it is reflexive. Everything is a subset of itself. It is transitive. If A is a subset of B and B is a subset of C, then A is a subset of C. And it is antisymmetric as well, because if A is a subset of B and B is a subset of A, we know that A is equal to B. So these are a few examples of partially ordered sets, where here on the first example, we have all the divisors of 12 as the set, and the relation is the division relation. In the second example, we have the set of all subsets, and the relation is the subset relation. Now, we just saw that we can have such kind of pictorial representations of posets. So natural question is, can we draw like all such posets in this way? So luckily for us, at least finite posets, we can have such nice diagrams. So what is a diagram? A diagram is a graphical representation of a partial order. And where we, as I just said, we do not allow self loops, where we can always add them by reflexivity. So in some sense, the ranking goes from lower to higher. We can consider that in the diagram, the ranking goes from lower to higher. And as we have already seen, the edges can only go in one direction by antisymmetry. And of course, no redundant edges. And we can always find these such kind of missing edges by transitivity. So all those missing edges, we can, from that diagram itself, we can see which are related by transitivity, and we do not really need to add those edges. So such kind of a representation is basically called a diagram of a partially of a coset or a partially ordered set. So now what is the basis of like drawing such diagrams? What I just mentioned is kind of the intuitive way of describing such diagrams. The main basis of drawing such diagrams is the concept of covering relation. What is that relation? If AR is a coset, and consider X, Y in A, two elements in A. What we say that A is covered by Y or Y covers X if X is related to Y and there cannot be any elements in between X and Y. That's the whole idea. In other words, if X is related to Z and Z is related to Y, this would imply Z is either equal to X or Z is equal to Y. And the notation that we use is as follows. We would have some exercises in your tutorial using this covering relation, and there we would use this notation to denote the relation. So just to get an example, consider the 22 Summer Olympics, which was held in Tokyo in 2021, and consider the medal tally. So this is the medal tally of the first 10 countries that featured in that medal tally for Summer Olympics. And let us not go into the silver and bronze medals. Let us just concentrate on the gold medals given by each country and the total medals got by each country. Now this is taken from the Wikipedia, which gives you the actual, the order that is there in the medal tally. Of course, the silver and bronze are considered, medals and bronze medals are considered as well, and they have some kind of a reasoning, ranking. So in fact, it's a kind of interesting to how to come up with a ranking that is reasonable. That's also an interesting thing to think about. Like there are some pages you can see that which talks about how to come up with such rankings, let's say for the Olympics or some other events between the countries. So now let us consider one ranking as follows. We consider this as we know that to talk about partial orders or to talk about rankings, we have to have a base set. So let us consider this base set to be the pairs GX and TX, where GX basically denotes the gold medal won by the country X and TX denotes the total number of medals won by the country X. So we are considering those pairs, the number of golds and the total number of medals. So now if we consider this base set and if we consider this following order, define GX, TX is less equal to GY, TY, if and only if GX is less equal to GY and TX is less equal to TY. Here, what are GX, TX, GY, TY? These are nothing but numbers. And we have the natural ordering, the usual less than or equal to order among the numbers. And we are utilizing that order to define this order between the pairs. I'm sorry, we are using the same notation, so I'm kind of abusing symbols, but bear with me on that. So what we have is that GX, TX is less equal to GY, TY, if and only if GX is less equal to GY and TX is less equal to TY. So now a question for you. Is this a partial order? What do you think?
Yeah, I think so.
Think of the usual less than equal to is a partial order on N.
I think so.
Can you hear us from here?
Purbita,
Can you hear us?
Yeah, now I can hear you
Oh,
properly.
yeah, someone is giving the answer.
Yeah.
I think so. It is.
Yeah. Okay. So why is it so?
Like satisfies all the like reflexive and decimal and transitive properties for each of it, like, but
And what about antisymmetry?
yeah.
Yeah, sure. Because of the antisymmetry of the usual less than equal to relation. So it is a partial order. So now, given that partial order, we can have that diagram as follows. So if you consider the gold medals, 10, so just to show you, this is the table which we are considering. And accordingly, 10,33 should, given our order, 10,33 should be less equal to 10,36, should be less equal to 10,37, should be less equal to 10,40, and so on and so forth. So that is exactly what we are capturing. But now, if you think of 22,64, 20,71, and 27,58, once again, I forgot to put a bracket there, I'll change it. So can you tell me why they're like not comparable? Because the both conditions are not getting satisfied.
Yeah, 22 is greater than 20 and 71 is greater than 64.
22 is greater than 20, but 64 is less than 71.
Yeah.
So as you can see that certain elements are incomparable and certain elements you can compare if you consider that pair. So accordingly, you have this ranking of this 10 top countries in the Olympics according to the ranking that we gave. So here Great Britain, ROC, Japan are not comparable. By the way, I hope you understand what is ROC, isn't it? It's nothing but the Russian Olympic Committee. There's a history behind it whereby Russia cannot participate, but that's why we have this kind of Russian Olympic Committee or some such thing representing Russia. But let's not go into that history. So, but this is the partial order among the ordering among the countries that we have. And it's for, at least according to our order, it's not like not all the elements are related to all the elements. There are some incomparable elements as well. Now from this very real life fun problem to real life kind of more, what can I say, more kind of CS kind of problem, computer science kind of problems where you kind of schedule some tasks in some, let's say some industry or some company. You have to big time, these scheduling methods are big time problems in such companies or industries. So once again, POSITs play a role there. And so if you can think of this operation research, they kind of deal with methods, algorithms, efficiency, complexity. So as to improve some very complex decision-making processes. Or for example, this scheduling tasks where what to schedule, when and what should be scheduled to get something very efficient, like maintenance of processes or efficient completion of tasks. For whatever reasons, we often need to do this, or this industry, not us particular, but these industries and companies often need to take care of this. And these are these PERT and CPM methods. If PERT and CPM methods are from the 1950s, they are pretty old methods, but they are still followed in certain places, such methods, and such is their importance and such is their effectivity. So in both these methods, the sets of scheduled tasks, they form posets, or these partial ordered sets that we talk about. And this is just an example of such a kind of a scheduling problem. And what is the worst possible situation, or how long will a task get completed if we could go through all the kind of subtasks and things like that. All such things can be given by the longest path, which are kind of given by some such maximal chains. Here a maximal, I will just get into maximal chains, but you can just see that this red arrows is giving the maximal chain, which is kind of the critical path in this process. It's called the critical path in this schedule. And so they are given by certain maximal chains in posets. But of course, the question is, how do we define such maximal chains? Okay, without further ado, let's talk about chains in posets. So there are various names for chains in posets. They are also called total orders, linear orders, or chains. Okay, so what are they? Now take any non-empty set. A binary relation R is said to be total if for any x, y in A, either x is related to y or y is related to x. Of course, it is both possible for both to be true, but for posets, it's not possible for both to be true, but in general, it is possible for both to be true. Now, if you consider that total relation in a poset, we call that relation to be a total order. So if we consider any non-empty set, a binary relation R is a total order if it is a partial order as well as it is total. So that's what we talk about. So that's how we define chains or total orders. For example, if you consider n the set of natural numbers, of course it's a total order. And in fact, you can think of the sets of words with kind of alphabetical order where A is less than B, less than C, less than D, and so on and so forth. This is kind of the way you get to see the order of the dictionary. So this is also kind of an example of a total order. If it's not clear just now, you can think about it, how you will get this order to be total. Okay, so these are some examples of total order. Now, a very related concept is those of anti-chains. It is the complete opposite of chains. What are they? Take any poset A. A is an anti-chain if for any x, I'm not able to click on the chat. Can somebody tell me what is the question? I'm sure there is some question.
Just a moment.
There is no question. I have just posted that they can ask questions.
Okay. Thank you, Amit. Yeah, so I'm telling again and again, like, please do interfere. Otherwise, it will be so monotonous. I'm lecturing and I'm never in fond of monotonous lectures. So please do interrupt whenever, if you do not understand something. Okay. So what is an anti-chain? Anti-chain is the complete opposite to chains, which means that no elements are related. So they're related means it's no elements are related to each other. No pair of elements are related. Okay. Of course, it's also, you can think of it as a poset because all the conditions are satisfied. So for example, any set with the discrete order, if you think of an example, meaning X is just related to itself and nothing else. So in some sense, some kind of isolated points you can think of. This concept we talk about as anti-chains. Now, I'm once again and again, I'm delivering various definitions and various examples. If you are hearing for the first time, it might be like too much to get stock of all these definitions of at a single go. But of course, the slides will be there, and I will post the slides immediately after the talk. So I will send it to the organizers so that they can be posted. And please have a look at the slides. Even if you are not able, if you think that you want to read it over and ask me questions, I'm available all through the school. Even if it is you are not understanding something, or you want to think about itself before you ask me anything, you are welcome to do that as well. But anyway, so let me continue with all these definitions that you like kind of need to have in mind to get into the other topics in the school. So there is a level before the partial order, which I will be talking about now. That is the concept of pre-order. What is a pre-order? Any reflexive transitive relation on A is said to be a pre-order. If it is antisymmetric, in addition, we say it to be partial order, but it doesn't necessarily have to be antisymmetric. Such a relation is pre-order. Now, consider this example, Z, the set of integers with the divide relation. Generally, we said, when we talked about the divisors of 12, the set, we saw that it is the relation is antisymmetric. But why am I saying this relation is not antisymmetric?
Because A divides minus A and minus A divides A.
So this is an example of a non-antisymmetric relation, but of course, it is reflexive and it is transitive. Should be Z minus 0, but bear with me. Now V, the set of all vertices in a graph. And what is this reachability relation? So we call, let's say U and V be two vertices in a graph. We say V is reachable from U if there is a path from U to V. Now, of course, if you just give the graph in general, if there is a path from U to V, let's say a directed path, there is no harm in having a directed path from V to U as well, which basically constitutes a cycle at U. So in general, this reachability relation, if you consider like loops, and if you consider vertices where there are kind of loops everywhere, and if you consider this reachability relation, if you can think about that X is reachable from of course X is reachable from X, and then if X is reachable from Y, if Y is reachable from X and Z is reachable from Y, then X is reachable from Z is reachable from X as well. So it is transitive, but of course it's not necessarily antisymmetric. Any question here?
No question from here at least. But what about the online participants?
No, I'm just taking some, we should have some questions and some interactions. Of course, there might be too trivial to ask questions for now. Okay, so let's continue. Now, given any structure, now, what are the things that we kind of first talk about regarding these structures? For those students of mathematics, when we talk about groups, we talk about subgroups as well. So when we talk about rings, we talk about subrings. When we talk about fields, subfields, and when we talk about, you will be hearing topological space about topological spaces in the next lecture. When we talk about topological spaces, we talk about subspaces as well. So whenever there is a structure on a set A, which we have here, the coset structure, a natural thing to talk about is the substructures, or like what kind of subsets would have a similar kind of structure. So that's a natural question. Of course, as we see that in groups and other areas, not all subsets will form subgroups, or not all subsets will form subfields, rings, topological spaces, something we have to consider. Okay. Sometimes all subspaces, all substructures will form the same structure. Sometimes it is not the case. So the question is, what happens in terms of posets? So if you consider a poset A comma R, where A is the non-empty set and R is the order relation on A, and take any non-empty set, the restriction of R to the set B will form a poset as well. And this restriction is kind of called the induced or the inherited order on B. So it's any subset with the restricted relation, we have to think of, like, if X, for all X, Y, Z, for all X, X is less equal to X, X in B, X should be less equal to X. For all X, Y in B, if X is less equal to Y and Y less equal to X, then X should be equal to X, Y. And of course, transitivity. For all X, Y, Z in B, if X is less equal to Y and Y is less equal to Z, then X is less equal to Z. So we have the same relation, restricted relation will form a poset as well. And in fact, if we have the total order for A and R, the induced order will form a total order as well. Okay. So when I'm talking about structures, one concept is definitely substructures. The other concept is morphisms or structure preserving maps. So the way the morphisms are related to the base structures, it's really interesting, and you will study a lot more about it in your category theory course. But for now, let us restrict to morphisms on the posets or structure preserving maps on those posets. So if we consider A and R and B and S be two posets, and if we consider F A to be a map, F be a function from A to B. Now, F is said to be order preserving. Don't worry, I will get into the example soon, but let me just kind of give you the definition, which is a natural one. It preserves the order structure, meaning if X is related to Y in A, then Fx should be related to Fy in B, which in other words, if X are Y in A, then Fx S Fy in B. So that is what we call to be order preserving or structure preserving. Now, F is said to be an order embedding if both the things happen. If X are Y in A, if and only if Fx S Fy in B, meaning if X is related to Y in A, if and only if Fx is related to Fy in B. Okay, so order embedding is another way to talk about order embedding is an injective order preserving map. So from this condition, you automatically get that it is injective. So another way to talk about is injective order preserving maps. And if somebody doesn't know what an injective function is, it's nothing but if X is not equal to Y in A, then Fx should not be equal to Fy in B. That's the idea of F being an injection. Now, of course, F is an order isomorphism. and we say that A and B are isomorphic or ordered isomorphic if F is an order embedding of A onto B, meaning it's a surjective map as well, meaning for every element Y in B, there is a pre-image X in A, which means that for every element Y in B, there is an element X in A such that Fx is equal to Y. So that is the idea of the onto. So the idea of order isomorphism is it has to be order preserving, and it has to be a bijection, or it has to be an injection as well as a surjection. So this is something for you to think about. Maybe we can come back to this question in the tutorial session. Is every bijection from A to B, does it necessarily have to be order preserving? That's the whole idea of this question, isn't it? Is every bijection from A to B an order isomorphism? Okay. We will come back to this question later, maybe in the tutorial session. Now, let's give some example. We are just overflowing with definition. So let us work on some examples. So now consider N, A to be the set of natural numbers and B to be the set of integers. And both of them, we consider both R and S to be the less than or equal to relation. So then the inclusion map is, of course, order preserving. In fact, it is an inclusion map means for all x, ix equal to x. Okay, is of course order preserving, and in fact, it is an order embedding. But of course, not orderized. Okay. Now another example, if we consider the set of all subsets of these two happy faces and these two angry faces. So this, the left diagram gives you the set of all subsets of the happy faces, and the right diagram gives you the set of all subsets of the angry faces. So then you can think of this following map, which actually gives you an ordered isomorphism. Any question here? Okay, since there is no question, let me force you to say something now. Now, it's completely up to you. You have these 6 definitions of mappings or functions from different cosets. Tell me which are order preserving, which are order embedding, which are order isomorphism. First of all, consider phi 1. What can you say about phi 1? What can you say about the phi 1 map?
Is it visible to all of you?
Yes.
I think those on online, it's visible to all. Maybe for the offline people, it might be a bit smaller.
Is it visible now to all of you? Fine.
Yeah, no more talking by me. Now it's over to you. Come on, tell me, what can you say about phi 1?
It's not. It's not. None of it.
It's not what?
Neither it's order preserving.
It's not order preserving. Exactly. It's not order preserving. Everybody clear?
All of you get that point, that why phi 1 is not order preserving? Okay, fine with phi 1. Yeah.
No, ma'am.
Yes.
Can you explain why is it not order preserving?
See, A is less equal to B in this order in the left hand poset. Now, is phi 1A less equal to phi 1B in the right hand poset? Tell me. Yes or no? So what is the definition of order preserving?
Was it Angshika?
I'm order preserving was if X is related to like.
If
Y,
X
then
is related to Y, then Fx is related to Fy.
Yes, ma'am.
So does that condition getting satisfied by phi 1? What is the relation in the left posets? A is related to B. And what is the relation like, or A is less equal to B?
Only when A is related to 5 and D, I think.
No, see, there is an ordering. If you like, so if we, when I talked about the diagrams, these are all represented by diagrams, isn't it? I'm glad you asked me this question. So these posets are represented by diagrams. And as I mentioned, the elements appearing higher in the diagrams are kind of higher in rank. It's not about just the relation, it's an order relation.
Okay. Actually, ma'am, I missed the beginning of the lecture, so maybe that's why I don't understand how.
No, so it's related, definitely. But the thing is that if, in some sense, if you think of A to be 0 and B to be 1, 0 is less equal to 1. So then if you have for phi 1 to be order preserving, phi 1 0 should be less equal to phi 1 1. Okay. But if you see the right hand side, then there is this straight line. So then the order is what? Phi 1B, like here.
Is less
A is below B, which means A is ranked lower than B. So phi A should be ranked lower than B. But as you can see in the right hand side, phi 1B is ranked lower than phi 1A.
Okay, ma'am. Yes, ma'am. Yes, I got it. Thank you, ma'am.
Okay. Now, for if you can yourself check that phi 2, phi 3, phi 4, phi 5 are all order preserving. Please check it yourself. But what they are not?
None of them are order embedding.
Exactly. None of them are order embeddings. And what can you say about phi 6?
Phi 6 is ordered embedding, but it's not order isomorphism.
Exactly. So, thank you. So, is it clear to everybody? Yes, no, something I'm waiting. I neither can see your faces, nor I can see my face. Nothing I can see.
What happens for the offline participants? Is it clear to all of you? It's clear from here. So I don't know about the online participants now.
So online participants, please speak up. I have some things on chat. Can you please tell me?
It's just everyone, someone written. Oh.
Sorry?
Yes, from everyone.
Okay.
Or two of them told yes, they can understand.
So I feel that somehow it's clear. So I hope the idea of order preserving, order embedding, and order isomorphism is more or less understandable to you now. Okay, so let's continue. So before going any further, let me mention a few things about notation. From now on, we will just, if the R is understood, we will generally use to denote R by less equal to. And of course, we will not always use the pair A comma less equal to. We will just use A to denote the poset. And the strict order, by the strict order x less than y, we mean that x less equal to y, but x not equal to y. And we will use x less equal to y and y. It's the same thing. Saying x less equal to y and y greater equal to x. It's saying the same thing and we will use them interchangeably. Okay. With this, let's continue. So this school is all about duality, and duality occurs right at the beginning, meaning there is a duality, there is a dual poset concept here itself. So how do we define the dual of a poset? So given a poset A, the dual of A, which we denote by A delta, is nothing but the underlying set will be same as A, but x will be less equal to y in the dual of A if and only if y is less equal to x in A. So that is the dual of A. That is the definition of dual of A. Don't worry, we'll soon get into an example. And generally, with this concept, automatically, if you think of some statement S about A, you can easily construct a dual statement S delta about A delta by replacing each occurrence of less equal to by greater equal to and vice versa. So how are we constructing the dual? We are constructing the dual by just taking the opposite relation. If x equal to y, less equal to y, we take y is less equal to x. And then automatically, given any statement, given any property, you can talk about the dual property as well, where you replace less equal to by greater equal to and greater equal to by less equal to, whatever be the case. So once again, I will soon give you an example. Now, if you think about some statement, so some statement which will hold in A, let's say S holds in A, then its dual statement S delta should hold in A delta and vice versa. If the S statement holds in A, then the dual statement or the dual property should hold in A delta. Now, if you consider some statement that is true for all posets, then its dual statement should also be true for all posets. You can easily kind of like solve it out. If you are not convinced, you can write it down how you can prove that. So if you take any statement S in A, then its dual, and that holds for A, the dual statement will automatically hold for A, the dual of A. And if some statement is true for all posets in general, so then its dual statement will also be true for all posets. So think about it. If you are hearing for the first time, you might not able to get hold of it just automatically, but please think about it. And if you have any doubt, please don't hesitate to ask me. Okay. So as I just mentioned, duality occurs at the very beginning, at the very first concept, at the very first structure that you are learning, this concept that is there. But it's some kind of a dual concept. Let me just put it this way, some kind of a dual concept. So for example, if you consider this lattice A, what would the dual lattice, if you consider this poset A, it's not even a lattice. If you consider this poset A, what would be the dual poset? What would be the dual poset? How would the dual poset look like? It would look like nothing but this. Are you all with me?
Yes.
Yes, sir.
So automatically, as you can see that what is a statement that is true for A? So there exists some element which is less equal to, so there exists x as that for all x less equal to y. And automatically, what is the dual statement of that? There exists X such that for all Y, X is greater or equal to Y. That holds in A dual. And that's exactly what I was talking about. Am I making sense? I have some more comments on chat. Is there any question?
Let me see just a moment. So there, just yes, they
Okay,
told yes.
good. So this is why what the dual coset or dual statements are all about. So as you can see that we just now have this element, which is the least element in A, and another element, which is the greatest element in A dual. So that kind of leads us to the concept of bottom and top, least element and the greatest element kind of leads us to this concept of bottom and top. So what are they? Take any poset A. A will have a bottom element if there is this bottom bot in A. I will denote this symbol by bot. Then this, what is the property of this bot? Bot is less equal to X for all X, which is a natural intuition of being a bottom element. Similarly, A has a top element if there is an element top such that X is less equal to top for all X in A. So like this other example that we saw, it has a bottom element and A dual has a top element. Now, if you consider this power set of X with the subset relation, as we saw earlier, it forms a poset. It's reflexive, transitive, and antisymmetric. Now, empty set is the bottom element and X is the top element in this poset. And if you consider any finite chain, or basically, let's say 1, 2, 3, 4, n, where 1 is less equal to 2, less equal to 3, less than 4, and so on, less than n. It has both top and bottom elements. So one is the, in this example, 1 to n, 1 is the bottom element and n is the top element. And if you consider Z with the usual less than order, it has neither a top element nor a bottom element. In fact, Q, R, neither, whereas N has a bottom element, but not a top element. So you can think of all these examples. Now, a related notion is that of atoms and coatoms. So the idea is we have the bottom and the top elements. Now we are concerned with, we can think of the elements which are just above the bottom element and the elements which are just below the top elements. These atoms and coatoms concerned with those kind of elements. So what's the definition? Suppose A is a poset with the bottom element and take any A belonging to capital A. So A is an atom in A if for all B which is in A, B is less than A, implies B can only be bottom. So A, there are no element less than A other than the bottom itself. Okay. So when that element is called an atom. And dually, if you have the top, A is a coatom if for all B belonging to A, B greater than A implies B equal to top. So as I just said, it's just the elements above the bottom and the elements below the top. That's the whole idea of this atoms and coatoms. So let's look at an example. Okay, before going into the example, let us consider the related notion of atomic posets and coatomic posets. So once again, take any like A to be a poset with bottom. Atom, let ATA denotes the set of all atoms. And when do we say A is atomic? if for any A, which is not the least element or not the bottom, there exists at least one X in the atom set with X is less equal to A. Okay, please go through it. If you have any question, please ask me. A is said to be atomic. The capital A is said to be atomic if for all A inside A, there is an element in the atoms below that element. It's kind of everything you can start off from the atom itself, from the atoms itself. All the elements you can start off from the atoms. That's the underlying idea. You will hear more about it later in the course, I'm sure. But is the notion clear? I will soon get into an example. Is the notion of atoms and being atomic clear? Yes, no?
Yes, from here. And I'm just going to check the chat.
Similarly,
Yeah, yes, from
similarly, we can talk about the notion of coatoms of A, and similarly, the poset is coatomic. We say if for all A with A not equal to top, there exists an element X in the coatom such that A less equal to X. Once again, it is covered like kind of the atoms for the coatoms, those elements form a kind of an, what can I say, umbrella over it. And for the atoms, they kind of form a trough kind of a thing inside A. So if you want to visualize it, that's how I would visualize them. So that is the main idea. Yeah.
Yeah, so I have a question. I like an intuitive question. I haven't worked upon it yet. So can we say that a poset containing a bot, if and only if it is atomic, something like that?
No. Think about it. Thank you. It's a very good question. It doesn't mean that poset containing bot will always be atomic. Okay.
Okay.
If you think of like, yeah, there are examples. And in fact, if you think about, let's say Q, okay, let's say all the rational numbers. And if you can, yeah, you think of all the rational numbers over 0. Okay, it has a bottom, isn't it?
Yes.
0 is the bottom. Can you think of those atoms? And even if you can consider an isolated element added to it, which is an isolated element, you can still think of a poset with the Q plus union 0 as well as that isolated element, and think about the isolated order. Okay.
Okay, thanks.
Yeah. So there are all kinds of, I won't say these examples are natural, but you can find like unnatural kind of examples where they won't equate. Am I making sense? Am I making sense?
Yes.
If not, please ask. Please don't hesitate to ask if I'm not making sense. I'll be happy to go into it again. But anyway, let's continue. If is there any particular question, Purbita, in chat?
No, it's just yes, nothing. Oh, it's just a yes, nothing else.
Okay. See, Obijit, you can find all such examples in infinite posets. Finite posets, if you think of it, they behave very nicely.
Yes. Actually. Okay.
Okay. You can think of all such examples when you think about infinite posets like Q. Sometimes when it's a discrete order, like say N and Z, it might work. But whenever it's a dense order, like Q on R, and you can think of subsets
Yeah.
where it might fail.
Sujata, there is a question from
Yeah.
Tanwar. Please explain atomic and coatomic by giving an example, ma'am.
Yeah. So here is your answer. So consider this set. As I said, it can be nicely explained with some finite posets. So let's consider this finite poset. Now, can anybody tell me what are the atoms here?
Yeah, just a moment.
So so somebody asked me not to give you an example. Of course, I will give an example.
The atom singleton A, B, and C.
Can you hear Sujata Di?
Yes.
The atoms.
What was it?
The atoms are singleton A, B, and C.
Exactly. So somebody, Purbita, can you tell me the name who asked this question? Give me an example.
Please. Oh, that's Angshika.
Angshika, is it clear to you?
Angshika, you can
Yes,
unmute.
ma'am. Yes.
Is it clear to you now?
Yes, ma'am. Yes.
Yeah, it is.
Okay. So A, B, C are atoms. And what about coatoms?
The cardinality two sets are coatoms.
Yeah, exactly. So these are the coatoms in this set. So this is all I wanted to say about coatoms, atomic, coatomic. I am sure you will get more insight into these concepts when I think Moa will deal with Boolean algebras and atoms in Boolean algebras, I presume. Are there any more questions?
Not from here.
Okay. No, there are chat. I see some new comments.
No, it's just about, okay, yeah. Someone, Shuyash, actually asked about, could you once repeat the example? So he wants to.
So is it, it's there on the board. Can you please ask me the exact question if possible? What do you want me to explain? I would be happy to explain.
Actually, ma'am, I was not able to hear the question due to internet connection. So.
No, the question. So it was that what are the atoms and what are the coatoms in this set?
Oh, okay, so the singletons were atoms and the cardinality 2 were coatoms.
Exactly.
Oh, okay.
So do you, like the atoms are, is that clear now, Suash?
Yes, ma'am.
Okay, thank you.
I have a question.
Yeah.
Yeah, so while defining atom in the partial order set, are we considering that it has only one bottom element or it can have multiple bottom element?
Meaning when there is a, okay, I will soon get into the maximal and minimality. For now, when we are defining the atoms, we are considering only one bottom element. Okay,
thank you.
For now, when we are defining the atoms, we will consider only one, the bottom element and the top element, where the bottom element is one which is less equal to all the elements. Okay. So I will soon get into the concept of maximal and minimal elements, which kind of says that there can be maximal there can be more than one maximal elements. But just to understand you correctly, when you are saying top and bottom, can there be more than one least and more than one greatest element?
By the definition, it cannot be because we have the antisymmetry properties. So if there are two bottom elements, then they are related to each other, and from there we can say that they are equal.
Yeah.
Same for the top.
Yeah. So yeah.
Like asked one thing, like, isn't it unique by antisymmetric property?
Exactly. That's exactly what Debanjan just explained. That
exactly. Yeah.
That's exactly answered by Debanjan here. So somebody named, I think Krishnendu Kaur asked me this.
Yes,
question.
yes, I got my answer. Yes.
Did you get your answer?
Yes.
Okay, fine. Okay, let's continue. So now, as I just said, I just mentioned, we'll soon get into maximal and minimal elements which is kind of, the idea is the same as top and bottom, but there is a difference. As we just saw that there can be only one top and bottom elements, but we are kind of extending that idea to get to maximal and minimal elements. And we will soon see that there can be more than one maximal element and there can be more than one minimal elements in a poset as poset. So what are these maximal elements and minimal elements? An element B is said to be a maximal element of B if B is less equal to X and X belonging to B, it would imply B equal to X. What does it say? It just says that there is no element in the poset above B. And similarly, for the minimal element, this is a formal definition, but what it says is there is no element of the poset. B is said to be a minimal element if there is no element of the poset below B. Okay. When it has a top and bottom, when a poset has a top and has a bottom element, it is automatically, it's a maximal element as well and a minimal element as well. But what happens if it doesn't have a top or doesn't have a bottom? So here you can see it has a least, the left hand side poset, it does have a least element, but it doesn't have a greatest element. And you can see the top two elements, you can think of them, these are the maximal elements of the poset. Similarly, on the right hand poset, the bottom two elements, you can think of them as minimal elements of the poset. Am I making sense?
Yes, from the offline mode participants. Yeah, Angshika also told yes.
Okay. Now, so that is the basic idea of maximal and minimal elements. So now what we would do, we would try to construct more, like how to construct more posets from given posets. We already saw one way of constructing more poset from a given poset. Where did we see it? We saw it in the dual concept. Whenever we have a poset A, there is this dual poset A delta, which gives us another poset, given a poset A. Now here, we are considering sum of two posets. When we are considering sum, we will be considering two kinds of sums. Now to start off with, we will consider this disjoint union of two posets. So what are they? To start with, we will consider A and B be two disjoint posets. What does this mean? The domain of A has no intersection with the domain of B. That is what I mean by two disjoint posets. But please note that this is not a serious restriction. Given any two sets, you can always think of, like given any two posets, you can always construct two posets which are disjoint to each other. So it's not a very serious constraint. And if you want to ask me that given any two posets, how will you consider a poset which is kind of like a disjoint union of these two posets, meaning how would you, given two sets, how would you consider a union which will, a disjoint union of two sets? We can go into it later. It's just about copying one set with pairing with 0 and copying the other set pairing with 1. Then given any two sets, you can get two disjoint sets, because the second coordinates will always be different. On the one set, it will be 0, and on the other set, it will be 1. So in this way, you can think of disjoint constructing disjoint union from two sets. But let us not go into all the technical details. So to keep our hands free, we will start off with two disjoint posets, meaning A and B, the base set of A and B has no intersection. Okay. Now, given two such disjoint posets, what is a disjoint union of these two posets? It's nothing but you take the union of both the domains, and how you define the less equal to relation in the union? You define it as follows. X is less equal to Y in A union B. If X is less equal to Y in A, meaning either X is, which we can define when X and Y are both in A, or X is less equal to Y in B, which we can define when X and Y are both in B. So when you consider disjoint union, what you do is, if you think of these two posets, the idea is just to keep these two posets side by side. So that is the idea of taking the disjoint union. This whole structure gives you the disjoint union of these two posets. Let's say left poset is a diamond with 4 elements and the right poset is with the 5 elements. And this picture gives you a disjoint union of the two posets, where now all these 9 elements are members of the poset.
Sujata, you do have 10 more minutes.
Yeah. Now, there is another kind of sum that we would like to talk about. It is nothing but the idea is the same. You take the union, the base set is the union, whereas when you define the order, once again, you do the same thing as earlier, like X equal to, for XY in A, X less equal to Y in A, or for XY in B, X is less equal to Y in B. On top of that, what happens is the right hand, like if you take the sum of A and B, the right hand poset goes to the top of the left hand poset, which means that in terms of ordering, if X is less equal to Y, then either both in A and both in B, and they follow the respective orders, or X is in A and Y is in B. So the idea is, as you see in the diagram, B sits over the top of A. That's the idea of taking the linear sum and constructing the new poset. Is the idea of the sum clear?
Yeah, yes, from the audience.
From the online people?
Yeah, they are also telling yes.
Okay. Now, we have talked about sum. Let's consider product. So this product is the same thing that we took in the Olympics example. So if we consider two posets A and B, the product is nothing but the Cartesian product of these two sets, and x1 y1 is less equal to x2 y2 if they have this relation coordinate wise. So x1 comma y1 is less equal to x2 comma y2 if and only if x1 is less equal to x2 in A and y1 is less equal to y2 in B. So now to give you some examples, let's consider these two chains. What would be the structure of the product of these two chains? So intuitively, you can think of, we would have this, the left chain has 2 elements, the right chain has 3 elements, so the product will have 6 elements. So intuitively, what you can think of is plug in the right chain into the 2 points of the left chain, which will give you 6 elements, and then give the associated orders. So if you work it out, you will see that, so you just need to plug in the one way of thinking about it. You just copy the right chain into the 2 points of the left chain. So you get 6 elements, and then you take the orders as defined by the given order. So in some sense, this will look like this. As you can see that we have plugged in 2 chains here, and then we have kind of have the orders accordingly as defined by the ordering. Okay. So this is the basic idea of the product. And just to give you another example, if you consider these three, the product of these two posets, once again, the idea is the same, plugging in the right poset into the 3 points of the left poset. As you will see that you get three, one on the top, one in the middle, and one in the right. This plugging in at 3 points, and you take the relation as is defined by the given relation. So this is how the product looks like. So in the exercise today, I have given some exercises on how would this product look like. So you can practice on your own as well. And even this you can practice on your own to see how the product looks like. Okay. Now, I will go into, in the remaining 5 minutes, I will just touch a bit into this very important notions in posets called the downsets and the upsets. And I will continue from here in the next class tomorrow. So what are these downsets and what are these upsets? The idea is very simple. Let A be a poset and B is a subset of A. B is a downset, which means that take any X in B, all the elements that lies below X should also be in B as well, in that sense. So which means that if X is in B and Y is in A and Y is less equal to X, then Y should also be in B. So the name kind of agrees with the definition, it's a very intuitive name given to this set. So similarly, you can think about upsets as well. Take any element, all the elements above that will be included in the upset. So B is an upset. I should have written an upset, but yeah. If X is in B and Y is in A and X is less equal to Y would imply Y is also in B. So for the downset, any elements below will be inside, and for the upset, any elements above will be inside, given any element inside that set. So for example, consider this poset. Can anybody give me an example of a downset?
Ma'am, set of natural numbers.
If we exclude F in this set and the subset obtained by that will be a downset, because yeah, it will be a downset.
Exactly. So you are saying A, B, C, D, E, G.
Yeah.
So
A, B, C, D, G.
Even A, B, C, D is a downset, isn't it?
Yeah.
So there
Also,
are
you
many
can consider the
examples.
set of all minimal elements.
In fact, the singleton set, the trivial example is the singleton set A or singleton set C. There are many such examples. I'm just giving one example, and your example is also correct.
Oh, ABC and AB given by Bhargav and Vinod.
Yeah. Yeah. ABC. There are many examples of downsets. I'm just giving a few examples. For example, similarly, you can think about upsets. G is an upset. And also now you can include F. E, F, G is also an upset. Do you agree? So I hope you all agree that E, F, G is also an upset. In fact, if you add D, it remains an upset. So here are the examples of upset. Some related concepts. We have the down X, the set given A, any poset A, we can define this down set X or down X, which is the element of all elements in A, which is less equal to X. We can define the upset or upset X or up X, given all elements Y, which are greater or equal to X. And then given any set, we can also define down B and up B similarly. What is down B? All such elements Y in A such that it is less than at least one, it is less equal to at least one element in A, in B. And up similarly, up B or upset B, all elements in A which are greater than at least one element in B. So you can think of all these sets, down X, up X, down B, up B. So how much time I have? Okay. So I should finish now. So, okay, let me just finish it with this notation. So you can think of the collection of all downsets with the subset ordering, which forms itself a poset, and that is given by order of A. And if A is an anti-chain, you can, order of A is nothing but the power set of A. If A is an anti-chain, then order of A is nothing but a power set of A. And if A is a finite chain, then you can construct order of A is the down X for each X union the empty set. You can think of it in this way regarding the collection of all downsets of a poset A. And for example, if this is your A, B, C, D, this is your poset, the order of A, order of this poset is given by this poset. The order of the poset OA for given this poset on the left hand side is given by the OA in the right hand side. Okay. With this, I end today's lecture. Thank you.
Thank you so much for such a nice introductory course on order. So there is I hope that I'm not going to take any question right now. So there will be a tutorial session at the end of the day. And now there is a 15-minute break for tea. And after 15 minutes, we are going to start with the introductory course on topology. So please get back here by 11:45. Thank you so much.
Tea will be served there. There is another session going on outside, so we don't have the space available. And if anybody wants to talk to the speaker, yeah, you are welcome to come here and talk.
Yeah, sure.
Yeah, thanks, Sujata. Thanks, Sujata. It was elementary enough, to, like a good introduction to the school. I hope everybody could follow. Am I audible, Sujata?
Yes, yes, yes.
Yeah, okay.
Audible. Thank you, Amit. I hope it wasn't too elementary.
Huh?
I hope it wasn't too elementary.
In the beginning, I thought so, but it's okay. But since there were questions, so I feel like it was appropriate.
No, because yeah,
Hey, John,
even there were questions on these stuffs as well.
Okay, I'm going out. Yeah, Sujata.
Yeah, sure.
Yeah.
Thanks.
पूर्विता, मैंने 13 कप टी लाया है और यहाँ पे 13 लोग हैं, फुल कप पी सकते हैं आराम से. So अरे है. प्रोजेक्टर बंद कर दो.
So the Zoom is all yours, so you can talk with each other if you wish to. So that's a good thing to do actually, if you want to. Am I audible to all of you?
Yeah, let me just tell everybody I'm here if you have any question.
Yeah, please talk with each other. That will make the school more interactive.
So I could see a lot of questions here, which I lots of questions, comments, answers to my questions, which I missed completely.
No, I tried to address.
Thank you. It was a botheration for you, isn't it?
No, it's fine because like over Zoom it is really problematic sometimes when you are lecturing. So it was my duty, so I had to. So is there any question, doubts, or you may actually talk with each other by just introducing yourself? I think that may be a good thing.
No, but everybody is kind of resting after this 1.5 hour talk. That is also there. And they have to be ready for another 1.5 hour talk, isn't it?
Another 1.5 hour torture. So you will be there in topology course or not really?
Yes, I will be there.
Oh, that will be great. So I can see like it was 35 of the participants and now I think almost 26 is there. So I hope that one breakout room or two breakout room we need. Maybe two.
No, we do not really need any breakout room.
That's the point I am thinking about. Like,
yeah.
So I guess that maybe Chandrima and Abhijit can take care about that online participants and Prashanjit and Bidhan can take care about the offline mode participants.
Yes, yes, sure.
Thank you.
So for those who are already here, can you please tell me whether the level was okay or was it too preliminary for you? Everybody is on mute, so I don't know.
It was just right for me, ma'am. Can you hear me, ma'am?
Yes. Thank you, Vinod. Okay, thank you.
Am I audible? Can you hear me? Hello?
Yes, you are audible.
Now is it, my voice is coming now?
Yes, your voice is coming.
Okay, very good. So I think I need to change the... ये कैसे करते अन्ना दो নম্বরটা এটা 1 করলে তো কিছু হচ্ছে না ও পাওয়ার অফ আছে কি হলো এটা পাওয়ার অফ আছে না পাওয়ার অফ নেই দেখ যাচ্ছে না আমি বোধহয় অফ করে ফেলেছি একবার প্রজেক্টর অন কর কারণ এখানে তো দিতে হবে ওই বোর্ড তো দেখতে পাবে না ভিডিও অন করা আছে না অন করা নেই ও আচ্ছা আই সি রাইট কি ব্যাপারটা আসছে Nothing is coming. Oh no, এটা আমি off করে ফেলেছি বোধহয়, এটা নেই বোধহয়। No, it is fine. So 1 নম্বর তাই তো?
ভিডিওটা অফ হয়ে গেল নিজে।
কি করে হলো এটা?
ভিডিওটা অফ করে দিলাম এই জন্য।
মানে 1 2 3 4টা করতে হবে বোধহয়। বোর্ডটা ভিজিবল কিনা সেটা জিজ্ঞাসা করতে হবে। Can anyone confirm that you can see the first board?
Yes, we can see, but maybe Purbita, you can write down something.
Yeah, I will write down. Yeah, I need to check the font, like what is needed to be understood. কতটা বড় করে লিখতে হবে সেটা দেখতে হবে।
That is too near the light.
Is it visible? The font is okay?
Font is fine.
Okay, so I'm not going to write down on that place. I will write down here.
Yeah. That is fine.
Okay.
That is okay for me.
So it's visible and audible, right?
Yes, at least for me, it's fine.
Okay. I hope that it's going on good with others as well. Okay. What is the time? 11:45. ওটা বন্ধ করা হয়নি বোধহয় না? মেরা হ্যায় এটা বন্ধ করতে পেরেছিস? কারণ ওটা বন্ধ করাটা একটু চাপের। দাঁড়া ওটা বন্ধ করি ঠিক করে। বোতলটা ওটা একটু চাপের আছে, ফট করে খুলে চলে আসবে না। আচ্ছা পুরা ঠান্ডা পানি in case I need to. Yeah, try to be in front, then it will be good for me too.
Yeah, firstly and afterwards. You are okay.
So when people will come in, then
You are sitting in the blind spot for the camera.
I think the mic is not properly working. It is just for the online audience, right? Sound कम किसका करना है? ये वाला? No, actually nothing is audible from here for the audience here.
It should be on the speaker.
No, I think it should be from here as well, right? But my voice is not coming right in the microphone. But they can hear me, I guess. All of them. Yeah, I do have all my. I mean, all my collar kind of. Oh, hi, Marcus. You can change the. What can I say? He cannot see us actually. Can you change the?
Hello. I can hear you.
Yeah.
Hello.
Yeah,
Good
yeah.
morning, at least. Hello.
Hi.
Oh, here. Hi. Hello.
Hi. Where is Amit? Yeah, Marcus is here. You may talk.
Oh.
Hi, Amit.
Oh, you.
Hello.
Yeah.
Hello.
I think you are.
I'm visible, right?
You are.
I can hear everybody very well.
You have to find ISLA 2022 in the list of participants.
No. He just told that he can hear everyone.
I can hear Purbita quite well, but I can't hear Amit very well.
Oh, because I do have my microphone with me.
Oh, yeah, right. Okay.
Yeah, it's nice to see you. It's very early morning for you.
Well, it's 7:15. It's
Right.
not very early, but I couldn't make the inauguration. It would have been 5.
Yeah. That I can imagine. Very nice to see you.
Yeah, nice to see you too. How many people are there in person actually?
We have around 15.
Okay, okay.
Yeah.
Show with the
Yeah, we can
camera.
show. We have, yeah, you can see a few people.
Not everyone, but some people went for the tea actually.
Yeah.
Yeah, of course, of course. Uh-huh. Uh-huh.
Yeah, this is one half and the other half.
Right. Uh-huh. Oh, yeah, okay.
Yeah.
But many people are on Zoom, I see. Yeah.
Yeah.
Yeah, okay.
But still very less than the number we expected.
Yeah, true.
And, we had like 160 registered participants now.
But
Yes.
we don't know because these are the preliminary courses.
Yeah, this is preliminary.
Right,
Yeah. Maybe
Yeah.
they will join for the advanced stuff.
But then maybe also people are coming later, maybe. I don't know. Yeah, exactly.
That's true. That's
Yeah.
true. Yeah. So I think we are about to start in like 2 minutes.
Yeah, okay. I mute myself.
Yeah. No, is Annai audible to all of you?
Yes.
Okay, very good. Oh, one thing I should tell all of you that in the website of ISLA, I have already put a lecture note on introduction to topology in the course materials section. If you want to give a look at it, please go to that website and see it. So if you have any problem, let me know to find that note.
Maybe you can share a link. I can share a link.
Yeah, please do that. Yeah, that will be better, I think, for all of the participants. Actually, I'm going to explain the contents, whatever is written in the lecture notes. So if it is with you, will be helpful. And of course, it will be more helpful during the tutorial session. Yeah, the link is here actually. I already shared the link. Yes.
So it's time to start the new session. I have a introductory session on topology by Purbita Jana. So she is working in the subject area of mathematical logic with the focus on categorical relationships among various vector spaces, algebraic structures, topological systems, and logics. Her current interests lie in the area of mathematical logic, ordered algebraic structures, model theory, category theory, topology, frame theory, and fuzzy logic. So she'll be talking about basics of topology.
Okay.
Over to you.
Yeah, thank you so much, Annai, for such a nice introduction. And I'm thankful to all the audience to come here. May I ask all of you that how many of you already went through the idea of topology and the course on topology? Could you please raise your hand, the online participants and from offline? I hope that most of you already, right? Okay. So I guess that very few of you are there who never went through the topology course, right? Am I correct? Anyways,
Yes, ma'am.
Okay. So anyways, today I'm just going to talk about some of the basic notions from topology. And of course, I cannot give you the much motivation. The subject is already rich itself. There are lots of motivations available to study this subject area. But our only motivation here is about to make ourselves enabled to go through the next lectures, whoever never saw the or never went through the course of topology. So I'm just directly start with the definitions and all, and I'll try to explain it, what the concepts are, and that will be enough for the next courses. So that is my main motivation to give that course to you. Okay. So first of all, you already saw one of the example of a set and its power. So what it is, say if you have a non-empty set X, so then what could be its power set? Power set of X is nothing but the collection of all subsets of X, right? So for example, if you consider a 3-element set, say A, B, C, then what will be the power set of X? I mean, what the elements will be there? You can understand that empty set always a subset of any set, and the set itself is a subset of X, right? So empty set and X should be there. And what else should be there? What are the subsets of this particular X? Anyone?
All subsets.
Yeah, all subsets. What are they?
A, B, C, A, B,
All
B,
the
C,
singletons,
A, C.
all the singletons, the doubleton, and that's it, right? And you can observe that if, I mean, whenever you have a given set and you are taking the power set of it, it has the ability to close any intersection, any union and complementation and so on, right? So you can see that power set is a very powerful collection of the subsets of X. Now I'm going to talk about the topology. So topology is what? It is a subfamily of power set of X, and I'll tell you that what kind of subfamily I wish to included in this subfamily of power set of X, so that I can call them, can call them in a special name, which is topology here. So the first one, what I'll demand from this family to be a topological space is that I will confine this empty set and X in this family. So I wish to, sorry for that, because I used to change those notations many times. Okay, so I want empty set and the whole set should be in the topology. Okay, I mean in the family to be called it as a topology. Second one is that whenever I have a subset A1 and another subset A2 in the family, I will always demand that you can see that A1 intersection A2 is another subset of X. If A1 and A2 are the subsets of X, then A1 intersection A2 is another subset of X, and my demand will be that it should also be inside that family. And the third demand is that if I have any number of members in that family, I will ask for this arbitrary union of this collection of elements from the family should be inside this family of subsets. If I can make a subfamily of power set of X, like satisfying these three properties, then I'll call this tau as a topology. Okay, it's a subfamily of power set of X, nothing more. So tau is called a topology on X, and the pair X tau will be called topological space. Okay, so one thing I would like to mention here, like whoever went through the course on real analysis at least or topology, they can understand these three properties are the properties of open sets. So whoever doesn't know about what is open set and all, don't worry about it. I'm defining it. So what is the open set here? By definition, the elements of tau will be called open set. That's it. Okay. And whoever went through the idea of the open set in the real analysis course, try to understand why these three properties will be enough to think about open set. That's it. Okay. So the elements of tau will be, is it visible, the bottom part? Yeah, for online.
Yes.
Okay, good. So the elements of tau will be known as open sets. Okay, So now one observation I would like to make, I wish you to think about that. Whenever I'll try to make a subfamily to be a topology, at least empty set and X should be there always, right? So if I have any X, and if I take only empty set and X, is it possible to think it as a topology on X? That means, will it satisfy all the properties, whatever I am written? Of course, first property is there, and second and third. So I think like online participants also can speak out, okay? Okay, anyways. So that is a topology, right? And whatever topology you want to make, at least these two elements should be there. So that is the smallest one, right? So this topology is the smallest topology. And also it is known as indiscrete topology. And denoted by tau ID. So indiscrete topology is the smallest topology on any given X, right? And next one, you can see that whenever I'm going to make my family to be a topology, I'm collecting the members from power set of X. So I already told you that power set of X also has the ability to satisfy all these properties. So that is also another topology, right? So for any given set, you are going to get always a topology, which is the power set of X, right? So you can see that I cannot include more elements here because I need to pick the elements from here to make a topology, right, on X. So that is the largest topology. And this is known as discrete topology. And it is denoted by tau d. Now let us make some topology in between, right? Those are very kind of trivial things. So let I already took a set X and I took a power set of X here. So let me collect one of the collection from this power set and let me know whether it has the ability to form a topology on X or not. I mean, given X equals to A, B, C. So is it, will it form a topology? Yes. So it will form a topology. I cannot see like what online people are answering. Okay. Oh, they did not yet. Okay. So I think someone, yeah, they are agreeing with that. It is a topology. Now I'm just going to give you another collection, say this one, MTXB. For the same reason, that will also make a topology, right, on X. And what about this tau 2, say? Will it form a topology? Why not?
Because AB does not belong to tau 2.
Yeah, because union of AB is AB, which is not inside the set, right? So this is not a topology, but these two are the topologies. And you can see that on a given set, you can define many topologies, right? And sometimes they are comparable, sometimes they are not. Why? You can always see that any topology on X will be in between this, right? Always. But we already saw two examples of tau and tau 1. They are not comparable in the sense that neither tau is inside tau 1 or nor tau 1 is inside tau. So topologies may be comparable, may not be comparable. So if they are comparable, that means if tau 1 is included in tau 2, then what we will call tau 1 is coarser or smaller than tau 2 or weaker than tau 2, and on the contrary, tau 2 is larger or finer or stronger than tau 1. So that is the idea about the comparison of topological spaces, or topology on some set, right? Okay, I'm just removing that part right now. So by now, whatever example I gave, is on a finite set. Let us think about some infinite set, right? Yeah. How many topologies? Yeah, that can be calculated, I guess, but no, for finite cases you are talking about. Yeah, yeah. So the thing is that if it is given, then I can list down those things. But for any number of set, I don't have the idea right now that how to say that how many of the. No, 3 I can, I think, because I can list down all of them. You're talking about what? Oh, yeah. Mm-hmm. Yeah. 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 The only thing we know that how many subsets will be there, that we know, but yeah. Among
like even number or something like that. I don't remember exactly.
Yeah.
But there are some scenarios for which we have developed formulas
to talk about that how many topologies, should be there for.
Be. I don't remember exactly.
For any finite number of sets, you mean?
No, I think it was about some special scenarios like 2n and
there is
4n,
some condition when 4n. You can talk about this.
Yeah.
Okay. So I'm not much aware about this type of things right now, but it is a good question indeed. Like people may think about it. At least for 3, we can calculate and see that how many of the of those choices will form a topology. So that can I know. Oh, it is not on maybe. Is it on? Okay, good. Okay, so okay, let me come to one and what can I say? One example where X is infinite. Okay. Say I am taking an infinite set and I'm building my collection of subsets of X like this. I'm including my empty set and I'm taking all the G subset of X such that X minus G is finite. This collection. So if I consider this collection of subsets for any infinite set X, then my claim is that this collection of subsets will form a topology. I'm not going inside that. The only thing you need to check that whether these 3 properties will be satisfied by this collection of subsets or not. This is in your tutorial, and if you stuck with that, you may ask your tutors, okay, and I'll help you with that. So my claim is that that will form a topology on an infinite set, and this is known as cofinite topology. Okay, now you can see that when I was considering the set as finite and constructing the topologies on it, then we could see that what the open sets are. Like it was really very clear view that what are the open sets, right? The thing is that like when I am talking about the infinite sets, not always it is the case that you can visualize properly that what are your open sets, right? And whenever we are talking about topology, we are actually dealing with the properties of open sets in some sense, right? Because the members of tau are the open sets. Now the thing is that a question becomes like that, is it possible to construct a topology from a fewer member of the topology itself? That means just studying fewer members, can I construct the whole topology and talk about that topology or not? So that is a question to boil down this thing in some lower level. So it's just like I just can come with some example I can give. It is, don't take it very seriously, but it is kind of an analytical thing. Like when we are going to build a house, then we need some raw materials like bricks, sands, cements, water, and then we have to use some technology and process to build the house. And if I ask that whether this building is very, strong enough or not, or how kind of building you can make out of this raw materials, you just need to see that how strong your raw materials were, how strong your techniques were, kind of, right? So similarly here, when I am talking about topology, if I want to build my whole topology from some pure collection of sets, then what operations I do have in my hands. Two operations at least by now. One is arbitrary union and the second is the finite intersection, right? So now it comes to the idea of base. Okay. So base is what? By definition, base is a collection of subsets from the topology tau, of course, given a topological space x tau. Whenever you have a given topological space x tau, the collection, I mean subcollection from tau will form a base, if any member from tau, say G from tau, can be written as the union of some members of the collection B, I mean the subcollection B from tau. So the thing is that here I'm just applying my operation arbitrary union. With the help of that, if some subcollection has the ability to form a topology, then that subcollection will be known as the base for that topology, right? So the thing is that you can understand that sometimes what happens, if you have a given subfamily, and if one will ask you that whether it is a base or not, so that time always using the definition will not help you. Sometimes you need to see that what properties of these subcollections are there, and then you can classify this, and then you can check it easily, right? So that is why I am going to talk about two theorems. One of them I will give the proof, and other one will be in your tutorial session, but it is a consequence of that proof only. So any intersection, any union, arbitrary union. So there is no restriction on that. If I apply my intersection, then it should be finite because I do have that only in my hand, right? Okay, so the theorem tells us if I have a given topological space, a collection B of tau is will form a basis or is a basis for tau if and only if the condition tells us that for any G in tau, that means for any open set and any members of G, there exists a member in B such that U belongs to B, which is totally included in that open set. So pictorially, what it tells you that if you have a topology on X, I'm calling that family will form a base if for any open sets in X and any member here, I will always, there is another chalk here. So I can always find a B which lies in the family, contain this point and content in the open. So if it happens for any open, then
U belongs to G.
U
contained.
Where?
U.
Oh yeah, U belongs to G. Yeah, thank you. So that is U belongs to G. Yeah. So that's the point in G. Yes. So that is the idea. Like whatever subcollection of tau will form a topology has this property and other way around. So can you readily see why it is so? Anyone? Is there anyone who cannot realize why it is so? No. Okay. Are offline participants audible? I hope not, maybe. But anyway, so let us see why it is so. Say I have given this property. I have given this property. I want to see if this property is given, whether that subcollection with this property forms a basis or not. So if I want to show that, B indeed forms a basis for tau. That means what? That means for each G belongs to tau, G can be covered by some of the elements of PIs, right? That is given to us. Sorry, that we need to prove, right? G equals to union of some of the elements from that collection. What we know from the given hypothesis, we know that for each U in G, for each U in G, I'm getting corresponding BU from B. BU belongs to B such that U is in BU, which is a subset of G, right? Now what to do? I need to prove that G equals to union of some BU, right? So what is actually G? G equals to the union of all those U's, right? And U are from BU, right? For each U, I'm going to get a base elements. So that will be a subset of corresponding BUs, union of this, right? And we already know that each BU is a subset of G. So union of BU also a subset of G. And you can see that G equals to G. That's why G equals to union of such BUs. That's why, and it happens for each of the open sets in tau, right? So, Vinod, did you get the idea? You may unmute yourself to talk with me because it's very tough for me to come here and see the chat.
I don't think he had any question.
There was no actually when I asked.
So that was for my question. Are offline participants audible?
Oh, I'm so sorry. So that part is understandable, right, for everyone. So I don't have to do it because all of you already knew what is going on. And I hope that if you have given that it is a basis, then it should happen. Is it clear to everyone? I hope yes, right? So that is the idea. Now come to the next theorem, but I'm not going to prove it, but I can just give the hint that it will totally depend on this result. So what it is, by now I was talking about, I have a given topology and I was collecting some of the elements from the tau and telling that whether it is going to make a base of that topology or not. Now I'm going to talk about like when given any subfamily from power set of X, can I verify whether it is a basis or not? So that is the idea of that theorem now. So this theorem will tell that a subfamily B of power set of X will form will become a base for a topology, for some topology, if that subfamily will contain the empty set. So empty should be in B. Second one, there exists some elements from the subfamily which can cover your X. That means X equals to or subset equals to whatever, you can do any one of them. So union of BI for some BI sitting in that family. And the third one is about, so let me make the picture first and then I'm just going to write down mathematically. So third demand is like that. If you have the set X and if you want to take the subfamily of B, I mean subfamily of subsets of X from here, then the subfamily will be like that. If you have any two intersecting elements in the family, so if B1, B2 are any intersecting elements in the B, then whatever elements are there inside this intersecting point, I can always find another element in the subfamily B3, say, totally included in the intersection and containing that point. It should happen for each intersecting points if there are some intersecting elements in B. So in Word, what can I write? Like for any B1, B2 from this family, if B1 intersection B2 is not equals to empty, then for any X in this intersection, there exists a third member in that family, so that X is in B1 intersection B2, sorry, X in B3, which is totally included in B1 intersection B2. So is it clear? Like when a given subfamily will form a base. So now what is the difference? Previously, I was talking about that I am just collecting some of the elements from tau, and I was talking about that whether it will form a basis for that topology or not. Now I am just talking about, like, if I pick any subfamily, then I have the tools to check whether that subfamily will become a base for some topology or not, right? So that is the difference between these two things. And in some books, actually, this is taken as the definition as well. So now let us come to some example. I told that base will help you to understand the kind of infinite, topology over infinite set of sets. So come to our favorite set, that is the real line. So set of all reals. My claim is that all collection of all open intervals will form a base of R. Are you agreeing with me? So if I collect all the open intervals in real line, AB means what? It is all the points in real, that is all real numbers, such that A is less than X, less than B. And on line, it looks like this, right? This kind of sets. So can anyone tell me that why it will form a base? Just checking the conditions to form a base for a topology. From the online participants, are you getting the points? I'm just asking to the online participants right now because I can't see you.
Maybe call some names. Check whether they are there.
Atri, are you there? Atri? What about Anand? Anand Taripatri. I know that he already knows those ideas. No one is there. Anand?
Yeah. I can hear
okay, Mir is there. You want to speak out? Yeah.
Good afternoon, ma'am.
Yeah, good afternoon.
Ma'am, this collection makes the base for the real line R, and the topology it generates is basically the standard topology that I have studied.
Yeah, that is true. Can you tell me why these three conditions should be satisfied by this collection of sets what I have given? That is the open intervals. Amit, can you please go to that? I don't know who is managing the camera. The third one. Yeah. Why this collection of subsets of R will form a base? Okay, particularly why second condition will be satisfied by the open intervals? Anyone from here as well? Can anyone tell me? Yeah. Yeah, X can be covered by which opens?
Like it will keep taking open set.
Yeah.
Like KB, and then we keep increasing bigger, and we will make it bigger. Then it will keep taking content.
Exactly so. So can anyone just concretize this idea? He already gave the idea, right?
Minus n comma n.
Yeah.
Open interval minus n comma n.
Sanjul. Yeah, that is also one answer. Yeah. So that is one of the concrete answer. And that idea, I don't know your name. What's your name? Nitish. Nitish actually gave us a very nice idea, like how to think about it, like how can we cover it. So one of the particular, there are many, I'm not talking that this is the only one. Like, so if I take these intervals over naturals, then of course I can see that it can cover whole real, right? My X is now R, right? I hope that you can realize the third property as well. Is it? Is it the case for all online participants? Because I can see the offline participants and I can understand they could realize. Can you please give the answer whether you are getting it or not? If not, you may stop me and ask me the question. I can make it clear because those are very primary ideas you need to know. What was Nitish's idea? Nitish, can you explain it again over the mic?
The idea was to, like, let us consider interval AB. Then we can consider another interval that is bigger than that and it contains AB. And if we will keep making
some these and then these,
some CD, and we will keep making the interval bigger. And if we will keep making the interval bigger, ultimately we will get the R.
That is exactly concretized by this minus n and n, one of the particular example, but he gives the general idea. Is it clear now, Suyash, what idea actually Nitish gave to us? Okay, good. You can speak out actually, that will be better. Okay, anyway, so I'm leaving this, but please check it if you are uncomfortable with this kind of ideas. So,
excuse me, ma'am.
Yeah, yeah.
Ma'am, in the union, minus into ये जो interval है minus n and n, ma'am, we are taking n from the natural numbers. Can't we take n from any real numbers? That will also give us the interval of the real line.
Yeah. That is also the interval in the real line, right? If I consider naturals.
No, ma'am, I'm just asking why are we only considering the natural numbers? Can't we take any real number?
I told it, it's not the only one. It is one of the particular one. So one of you told. You can take it over anything, no problem. You can do it. Is it clear?
Okay, ma'am. Thank you, ma'am.
It's Alia, right?
Yes, ma'am.
Okay. Yeah, that's a good point. I already mentioned that it is not the only one. You can collect many other various ways. And the general idea is given by Nitish already. So you can take it over anything. Right? Okay. So now and of course, someone already told that the topology made by this species, this tau, is known as, oh, it is not visible. Okay. Known as standard topology. Standard topology or usual topology on R. Okay, so I gave two more examples of this kind of things to check that whether it is forming a basis or not in your exercise in the note, and you can verify it by yourself. And if you stuck with that, please ask your tutors during the tutorial session. So I'm removing this thing for now. Okay. So now come to the idea that because we just use the operation arbitrary union, we left about that operation finite intersection. So now the question is that can I form topology in some way so that I can use that operation finite intersection and build it. Okay. So then the idea of sub-basis will come. Just like in the example with what I was trying to make the analogy. So for the making a building, so you have the raw materials, you need to make the raw materials as well, like the bricks, another different operation. And the raw materials for bricks will tell you that how strong brick you are going to get or something like that, right? So here we are going to come with some idea of subbase. Okay, one thing I should say that base elements are actually indeed an element of topology itself. You can understand by that construction, right? And those are the special kind of open set. So those open sets are known as the basic open sets. Okay, I hope that I already wrote it in the note, but I just mentioned it right now. And subbase is what? Subbase is the collection of some of the subsets which has the ability to form a basis for a topology using just the finite intersection. Understand what I uttered? Is it clear? Is it clear to all? Okay, there is no response from the online. Okay, fine. So subbases, I'm not going to write it down because it is already in your note. So subbases are the sub collection even than the basis, and those will form a basis just using the finite intersection operation, and from basis using that arbitrary union we can form the topology, right? Can anyone tell me what could be the subbasis of like which kind of sets could we play the role of subbasis for the usual topology? That is the given base elements. I talked about AB, right? Those open intervals. So can anyone tell that which kind of sets will, I mean, have the ability to form this kind of sets just using the finite intersection? Yeah.
And the open interval start from B to infinity.
So you can do that right? Minus infinity to
Minus infinity to A.
Minus infinity to A.
Union.
Not union.
Means
You are allowed to do
open intervals start from B to infinity. If we are taking the collection of all open interval that are start from minus infinity to A.
Okay.
And
yeah. So you want to collect all those intervals, right?
Yes, yes, ma'am.
These intervals. And
Yes.
your claim is that that will form a subbase for the basis.
Yes, ma'am.
Right? Okay. So why it is so? Because you can write down this as this, right? Intersection of this. Am I correct?
Yes, ma'am.
So is it clear why the collection? What's your name?
Chandramohan.
Chandramohan. So what he gave the idea, like, is it clear that this collection of subsets will form a subbase for the basis of usual topology? Is it clear? Okay, fine. So that's the idea of the subbasis. Now I'll come to the idea of separation axioms, right? No, I will come to the idea about the closure and interior right now. Just a moment. Yeah. So I'm just removing this thing. So I just told you this, talked about these ideas because when you talk, you will go through the courses on the dualities and all, and when they will go from the algebraic structure to the topological structures, they are going to talk about the topology in terms of their base or subbase. That is why it is much needed to understand what are the bases, what are the subbases, how can you see a topology formed from this kind of collection of subsets, right? Okay. Now, I will talk about the closure and interior. So why I am going to talk about this? You know that in the previous course by Professor Sujata Ghosh, you saw that whenever you are talking about some properties, you are talking about some dual notions as well. So here actually we by now talked about just the open sets. Now we will come to the idea about the closed set. And actually I need this kind of ideas in my next courses. That is why I take the opportunity, not defining closed set directly from there, but I will derive it, okay, by the notion of these ideas, because these ideas will be needed in our consecutive courses. So to define a closure, first I will talk about limit point, and to define limit point, I will talk about neighborhood. Neighborhood of a point. Okay, so everything we are going to talk over a topology. So whenever maybe I will forget sometime, we are always given an topology and on which we are going to talk about everything. Okay, so what is a neighborhood of a point? So say I have a you can think about many analogies from your real life situation. I'm not going inside it because of the time limit. So you can think about that word, what does that mean? And I try to connect that, how it would be connected with the idea, not totally connected, but some ideas will match to remember. So say I have any point in X. So that is the small x. And which kind of sets will be the neighborhood of that point? I'm going to designate it. Okay. So subset, any subset of X is known as the neighborhood of this point if I can find some elements from tau. That means some elements from tau means I get some open set which will contain X sitting inside that subset. If I can give, if I can give you some open set which has that property around X, then that subset will be your neighborhood. Now my question is that whether this O itself a neighborhood of X, or given any X, how many neighborhoods you may get?
Infinite.
What happens? Oh, repeat the question. Okay. So my question is that whenever I have a given X, first my first question was that I need to give a open which will contain X and contained in NX, right? My first question was that whether this open will form a neighborhood of that X. And second question that how many neighborhood you can expect from a X? Like, is there a single one or many or what?
Infinite.
Can you see one of the neighborhood what I didn't mention here for that X?
Oh.
Okay. Can anyone tell me about one of the neighborhood? X itself, because it is an open itself, right? So X is a neighborhood of X, NX is the neighborhood of X if it contains such O, and that O itself is a neighborhood. And I can get any superset of NX and that will form a neighborhood, right? So for a given X, I can get many of the neighborhoods. And actually, I think that in the second lecture, Sujata Di will talk about this neighborhood system. I'm not going inside. I just try to portray the idea. That's it for now. And of course, then you will come up with the idea of filters and all, and this will give you some of the examples. So try to remember this idea. Okay, now the question is that what is the meaning of a limit point? Because I told you that when to talk about this, I need to define this, and for this, I need to define this, right? Now the thing is that limit point of a subset of X. So say I have a subset, any subset, it shouldn't be come from tau. It can be anything, right? So any subset, when a point of X in X, not in A, it can be in A, it can be on the boundary of A, it can be outside A. I don't know right now. So I'm going to define it. Then you can understand that where it should lie. Okay. So what are the limit points of A? So limit point X is the limit point. They can see it. Oh, sorry. Okay. Oh, okay, fine. So from here they can see, is it? Okay. X is said to be X, of course, from X, a limit point of a subset of X, which is A right now, if I collect all the neighborhoods around X. So it will be misleading, like when I give the definition, but just try to see what I am trying to say. So if I collect all the neighborhoods of X, and I am, say, NX are the neighborhoods of X, and if I intersect it with the set deleting this X. So A minus X, if X is not belong to A, then of course that is only A. And if it is belonging to A, I'm just removing that point from there. If that intersection is going to be non-empty for each of the neighborhood of X, then we will call that X is a limit point of A. Is it clear to all? What is the idea of that? So that is the idea of a limit point. Okay. Now come to the point. I just forget that what next I wanted to talk about. After limit point, I'm talking about the closed set. So now I am in the position to define the closed set. So closed set are all the subset of X, such that it contains all of its limit points. I hope that idea of neighborhood, idea of limit point is clear. Then you can understand if I take any set and if I can see that any limit point actually inside that set itself, then those set will be known as a closed set. So if it happens, then F is called a closed set. F is a closed set. So that is the idea of the closed set. And I told you that whenever I have a given definition of a open set here, I could talk about the closed set readily without going to the idea of closure and all. So what it is by theorem actually, if a subset of X is closed, if and only if its complement X minus F is open. That is X minus F is in tau. Of course, I have given a topology. Okay, so that is the idea, but you need to prove it because I define closed set in different way. And if I can prove it, that could be your definition. Okay, so that is the idea about the closed set. Now the closure of a set. So if I have a given set, given a subset of X, closure of A denoted by CL of A will be defined like what? So that is the smallest closed set which can contain A. So you can understand that it is kind of the similar idea of the cover what Sujata already talked about in her lecture, right? So it is the smallest thing, or we can say that it is the smallest envelope, a closed envelope, of course, of that set. So that means we can say that closure of A is nothing but intersection of all the closed sets which contains A, right? Such that it is a subset of A. Sorry, subset of, sorry, yeah, A is a subset of A, right? So that is the idea. So the thing is that whatever closed sets are around that set, I need to intersect them. Then I'll get the smallest closed set. Of course, you can get the guarantee if you calculate that intersection of any closed set will give you another closed set. So that gives you the guarantee at some point, and that will be your closed set which can contain your A, and that's your closure. So if I have a closed set, what will be its closure? So say F is closed. What will be the closure of F?
It will be F only.
It will be F only because it already contains its limit points, and that is itself a closed set which contains it, right? So that's the idea of the closure. Now I'm going to talk about, better to think about this, right? Like I already have that example, right? So can anyone tell me that this is a set of real, right? So what are the limit points of this? Closed interval AB. So what is the closure of this set?
Open interval AB.
Right? That is the smallest. So closed interval AB will be your closure of AB. So closure of AB is your closed interval AB. Right? So that's the idea. I hope that it is clear to you now. So now I am going to talk about the interior point. So of course, I didn't put any, like whoever went through the real analysis things, we already know that whenever we talked about open set, we actually defined it in terms of interior points, but I didn't do it here. I just do it other way around. So we have in our hand that what is the definition of open sets, and whatever you encountered in your real analysis course, like what is an open set, try to see that whether they matches or not. Okay, so that should be a good idea to do. Okay, so interior of a point, interior point of a set is what? So if I have a X, and if I have a set here, so when that X can be known as the interior point of A? Any idea? Can you understand from, I mean, any idea generated from your ideas when you just listen to that word interior? What could be? It is not a limit point. So you are talking about any open set, like this kind of things you are talking about. Yeah. So if you can find an element of tau, which is contained in A, and taking your X inside. So if it happens, then those X will be known as the interior of that set. Is it clear to all? So X is said to be interior if there exists, so X belonging to A is, where A is a subset of X, of course, is interior point, is an interior point if there exists an open in tau such that X is in O, which is a subset of A. So idea is clear, because this kind of ideas we are all, I mean, many times I already uttered this kind of ideas, right? So that is the idea of the interior point right now. So next, I think, okay, next the thing is that if I collect all the interior points for A, that will be denoted by int A. And if I collect all the, like if I take the, sorry, I have A and I have the closure of A. Closure of A means what? It will actually contains all its limit points, right? So can you compare these three sets? Of course, I already wrote it in the order. So interior of A is a subset of A and A is a subset of closure of A. Okay, that's it. I hope that we don't need much ideas about these things. But during the tutorial, you may ask your tutors that why, I mean, how can we define an open set with the help of interior only? Okay, so I am not giving that definition, but also you can form it, like you already know the definition. So how interior point will help you to define the open set, try to do it by yourself as well. Okay. Now I'm coming to the separation. How much time do I have? It's 20 minutes more, okay. It's 1:15, right? I will stop. Okay. So I'm going to, like, you can stop me anywhere if you feel that it is not clear to you. And I can repeat also. Okay, so next I'm going to talk about the separation axioms. Okay, one thing I'm just asking to the online participants, do you already have the notes with you? Then I'm not going to write down everything, but the board is not clear right now, I think. It's not totally visible, right? Okay, can you tell me that whether you do have the notes with you?
Yes, ma'am.
All of you, right?
Yeah.
Yes.
So then I'm not going to write down everything. I'm just going to talk about the concepts of the separation axioms. Okay. So anyways, so separation axioms, the name tells you that we are trying to separate something, right? So in our topology, I do have concepts of closed set. I do have concepts of the points. I do have the concepts of the open sets and all, right? Now the separation axiom will talk about when two different distinct points can be separated by some idea of open or something like that, because this is the tool in my hand. And also sometimes we will see that when a closed set and a point outside it can be separated, or any two closed set can be separated using the help of open sets, right? So first thing, the natural idea, can online participants see the diagram properly, because I can see the board is becoming hazy. Is it okay?
Separation axioms, that word is not clear, but that's
okay. That's okay. I'm just uttering it many times. So first of all, we are going to see that how can we separate two distinct points. So if I have a x, then if I have two different points, say x and y, I can separate them by one open, which will contain one leaving other, right? So say if I have some, like for any two distinct points, if I get a element from tau, such that it will contain X leaving Y. So that is kind of a separation to separate two distinct points, right? If it happens, then we will call the space as, of course, I have given X tau that I always need to mention. Then we will call that it's the T0 axiom, T0 is separation axiom, and that space will be known as the T0 space or Kolmogorov space. Okay, so next, how can I separate even in the stronger way? Like if I have a given X, I have two distinct points. It may happen that I can get two different opens. One of them is containing the first one, leaving the second one, and the second one will contain the second one, but leaving the first one. It will look like that. So say U is there. So some U and some V. It may happen that they are intersecting one, right? So that is, if it happens for each distinct pairs of points in X, then we will call that as T1 space. That is freshest space as well. So that's the idea about T1 space. Now I'm going to talk about another stronger one. So if you have two different points, it may happen I will get two disjoint opens from tau such that it will contain one of them, right? So that is another separation that is stronger than this, of course, in some sense. So this is known as T2 space or Hausdorff space. Now, can anyone tell me that which implies what? I mean, if T0 space is T0, should it be T1 or T2 or other way around? Whether it is T1, it will follow. Yeah. So according to you, T2 implies T1 implies T0. My question is that whether the opposite direction happens or not. So already my audience is telling that no. I don't know like what the online participants is stuff. They are talking nothing or just silent. So are you getting the points? I'm asking the online participants, is it understandable? Are you with me?
Yes, ma'am.
Yes.
Okay, very good. So the thing is that, can you give me one example which will be T1 but not T0? Just collect some finite things, like we already have X and power set of X, collect some tau from that Px and tell me that which tau will give you some T1 space but not T0. Can you form one? MTX and ABC you should mention. Who is giving the answer? Not you. You are the tutor, right? So any one of you other than Vidhan. So try to form one, like which will give you this kind of separation, but not that. Sorry, other way around. This one, but not that. Yeah, I'm sorry for that. So give me an example which is T1. Oh, I'm incorrect. Which is T0 but not T1 and T1 not T2. Yeah. That shouldn't take much time, right? Yeah.
So we will take X, phi and
X, phi
and
among
X
them,
slash
right?
singleton of A. It's, X slash singleton of every elements in X.
I'm not getting it actually.
Which means all the
closed
cardinality
sets.
to elements.
All the cardinality two elements. You are talking about this. AB, AC, and BC, right? Will it form a topology at all?
No.
Will it form a topology? If not, why?
No, it won't.
Why it will not form a topology?
The intersection.
Intersection is not here, right? So can anyone tell, like try to modify the example, then you can understand what is happening.
Ma'am, in discrete topology.
Who's that? Yeah, tell me.
Ma'am, X5 is singleton sets A, singleton set B, and the doubleton AB.
Okay, you are taking this. A, B, AB. Can anyone check whether it is a topology? We already talked about it, right? So is it T0? How it looks like actually, like you can make the picture. So that is your X, that is your A, that is your B, that is your C, and there is one open set around, I mean, A is an open set, B is an open set, and AB is an open set, right? Now try to tell me that whether it is T0 or not. You understand that picture, right? It represents that only. Like who gave me the answer actually? Alia. Yeah, Alia gave that example to us, and that looks like this. So is it T0? Why not? Because we need to check what? For each distinct points, I can get one open at least to separate them. So I have A, B, C, those are the distinct points. I can separate A from B by that open. I can separate AC by that open or this open, whatever. And I can separate BC from this and AC from this, right? So it is T0 indeed. Is it T1? Why not? Yeah, around C, I have only one open, which is the whole set and which contains everyone. I can't separate. So that is then one of the example, which is my, I always used to forget T0, but not T1. I'm correct, right? Okay. So anyways, so similarly, you can construct an example which is T2, and I mean, which is not T2, but T1. C cannot be separated. C cannot be separated from what? No. Because I need only one open. So one open, it is T0. That is why. It is not T1 because I can't separate C. Yeah, that is the idea. Is it clear to everyone? Which one? How it is T0. For T0, what we need to check? For each distinct points, I need to find one open which will contain one of the point but leaving other, just like this picture, right? How many distinct points I have in that example? A, B, and C. So A and B are distinct points. So can you see one open which can separate A from B? Just one open. What are the opens here? A itself. So A contains A but leaving B. What about B and C? B itself or AB, whatever. You can take that as well. What about AC? Now C is anything. So you can see that like X is my three distinct points ABC, and I'm just collecting the tau from here. So that we already saw that it's a topology, and I'm asking which separation is there in that topology, right? So the thing is that I do have only three distinct points. So I need to separate three distinct points by one open, like for each pair of distinct points, of course. So you can see AB can be separable, BC can be separable, AC can be separable. So everything is separable by one open. So that is why it is T0. Understand it? Clear? Why it is not T1? Our claim was it is not T1. So for T1, for each distinct points, I need to give the existence of two open, which may be intersecting, not intersecting, I don't care. But I need to separate them with two opens, right? So how many points I have? A or B are distinct? I can separate them actually with two opens, which is A and B. What about AC? So I have A and C. Containing A, how many open sets are there? Three open sets. One is this A, this AB, and this X. Those are the open sets containing A, right? And what are the open sets containing C? Just X, right? So I can't get different two opens which will contain one of them, leaving other, and I mean contain A, leaving C, and containing C, leaving A. So because C is sitting in the whole set. So there is no two opens to separate these A and C points. Similarly for B and C points. That is why it is not possible to be a T1 space, right? This separation should be applicable to each distinct points. each pair of distinct points. Is it clear now? Okay, fine. So that's the idea of the separations. And now I'm just going to talk about, do I included something on that? Okay, I have included, okay, now I'm going to talk about the different things. I already told that I'm going to separate 2 points or a closed set with the outside point from the, point from the complement of that closed set and 2 closed set, right? So next separation is like that. Say I have X and I have a closed set here, say F. So I have a closed set and I'm going to take a point outside X. When I can separate them means if I get 2, no, better to change my color. Okay, is it visible there? I can't understand. Mamit, is it? Okay, fine. So if I can find 2 non-intersecting open sets around F, non-intersecting around F and X, such that they can separate this closed set from the outside point. And if it happens for each of the closed sets and the elements from the complement, then we will call that space as regular space. So it's the regular space. Okay. Now regular plus T1 is giving you the T3 space. Okay. So that is the idea of the T3 space and regular space. Now come to the point of, yeah, Alia, ask. Okay, is there any? You can.
Excuse me, ma'am.
Yeah.
Ma'am, in separation axioms, we do not say the existence of at least one pair of open sets, or we say in general existence of open sets. Do we care about the number of open sets that should exist?
Number of open sets that should exist means I didn't get you actually. Can you just elaborate it a bit?
Ma'am, like in the previous example I gave about the topology on the set X, A, B, C. Then for one, yes, ma'am. Yeah. About separating, like you explained for T1 now.
Yeah.
You said we cannot separate A and C.
Yes.
Because for A there is existence of 3 open sets, and for C there is the existence of only 1 open set.
Yes. Yeah.
Do we not say like there should exist at least one pair of such open sets?
Yeah. If it happens for at least one pair of open sets, then it's okay. But it is not there actually for that particular example, because you can see that there is no 2 open sets containing A and C, right? In different opens, because C is only contained in the whole set, so everything is there. So I cannot separate it by the open. Understand what I am trying to say, or it is confusing to you?
I'm not understanding, ma'am, actually.
Oh, so what is your question really? Can anyone understand already Alia's question? Maybe I'm not getting her question in some sense.
Ma'am, I'm just asking if we come to the regular space and we are separating a closed set from a single point.
Yes.
And do we say
outside that closed set? Yeah.
Yes, ma'am. Do we say if there exists at least one pair of such disjoint open sets containing F and X only?
Exactly, yes.
Separately.
It is the case for everything, whatever I defined right now. For each distinct points, if I can give existence of at least one pair of disjoint opens such that they can separate, then it will be T2 space. That I told. Like,
okay, if there exists at least one pair, if only one pair is there, then also we can say that it's a regular space.
Yes, exactly so. Yeah, that's
okay,
the.
Okay.
Yeah, is it clear
Thank
now?
you.
Okay, welcome. Okay, so regular space is clear right now, I hope. So, and what is T3 space is clear. Now I'm going to talk about when 2 opens can be separated. So say if I have two closed sets are separated. So if I have 2 disjoint closed set, and if I can give an existence of pair of disjoint opens such that one of them contains F and another will contains the G. If it happens for each pair of disjoint closed set, then we will call that space as normal space. and normal plus T1 is nothing but your T4 space. Okay, that's the idea. So I already included plenty of examples in after that separation section, I mean separation axioms section. So you may work on that, like which are going to make your regular space, normal space, T1, T2, T3, T4, etc. But we can do one thing here. We can check whether the, like Alia gave that example to us, whether it is regular or normal. So how to check it? So for what can I say? For the regular space, what I need to see, I need to separate my closed set from outside points, right? So what are the closed sets? What are the collection of the closed sets here? The complement of empty is X. Complement X is empty. Singleton A complement is BC. And singleton B is AC. And that is C, right? Now what we need to do, we need to take that set, and outside that set, which points are lying? Just A. So can I separate BC from A? By the open, like what are given? No. So there is no possibility to be a regular space of that given example. Is it normal? For normal, what I need to do, I need to pick two of the closed set and I need to see whether I can separate them from each other by some pair of open, disjoint open. So can I do that, like for say BC and AC? We can't. So it is neither regular nor normal. Oh yeah, that is not. Yes, you are correct. Very good. Now tell me, like whatever closed set is there, none of them are disjoint. I had to separate the disjoint closed sets to be normal. Is there any disjoint closed sets here? So can I say this is a normal? Yes or no? One tells no and one tells yes. I think two of you.
Yes, we can consider this as normal.
Because I don't have any disjoint closed set, so I'm not responsible to separate them, right? So that is why it can be a normal space. So what happens with that? I already saw that is a T0 space, but not T1. Should it be T2? Not really. There is no way to be T2, and that is not regular, but that is normal, right? So that's the example you have, and you can work on the other finite cases by yourself, given in the note. And also I will ask you to think about the reals with the usual topology. What kind of separation it enjoys? You should verify. If you stuck with that, ask your tutor again. Okay. So that's it for the separation axiom. So I'm not going to talk about separation axiom anymore. How much? I think 14 minutes, right? More? Okay.
You might want to say that all singletons are closed, or
that's a tutorial program. I'm not going to inside that because it is maybe not much needed to understand the dualities and all. So I'm just going to cover all the things, whatever concepts you need in your consecutive lectures. I, of course, included many more other concepts which are not needed. That's why I'm not going to explain it. If you have any queries regarding those, whatever I included or outside, then you may ask during the tutorial. Okay. What I am doing, trying to do it, like I just jot down all the concepts, what is really needed to understand to make yourself enabled to cope up with the next lectures, the advanced courses on dualities and all. In fact, in the category as well. Okay. So next idea is about specialization. I'm not going to talk about it much. Just try to look at your note. I'm just going to say what is it. And it is why I am not willing to do that, because it is in the exercise of Professor Ghosh's tutorial session. But anyways, I'm going to explain what it is. And I can tell you that whoever came through the course of topology, they may not see that idea, because it is corely the ideas what actually whoever is studying non-Hausdorff spaces, they are working on it, and also algebraists do that work on this specialization relation. Okay, so if I have a given topological space, I can make idea of order there, just like how Sujata Di explained in her lecture. So using the idea of the open sets in the topology. Also, dually you can define this thing using the idea of closure of the set as well. So when I'll tell that two elements in X are related, so I will tell X is related to Y, like I'm just going to make it as a ordered set right now. Okay, so if X is related to Y, that means what? So we used to utter that Y specializes X, and I think algebraists used to think it in other way around actually. So anyways, it is written in the note, just have a look. And of course, I think Sujata Di also gave the definition in the other way, actually in the dual, like with the dual notion. I'm just going to give that idea with the open set because I talked about the open sets only here. So X is related to Y if for any open sets in tau, whenever X is in the open, then Y should also inside it. You can understand what I have written, like what are the relation between X and Y? That means Y may sit inside a open, X may not there, but wherever X is seated in the open, that open should contain Y. That is the idea. And dually, actually, the thing is that like if X is in the closure of Y. So that definition is given in the tutorial section. Okay, so you may see that why these two definitions are equivalent to talk about this relation, which is known as the specialization relation. Now tell me that whether this relation is reflexive, because I talked about a relation, you already know what are the orders. So is it reflexive? Yes, because X will sit in the same opens, right? So X less equals to X, so it is reflexive for all X. Is it transitive? Right? So this is also the case. X less equals to Y and Y less equals to Z, or X related to Y, Y related to Z implies that X is related to Z. That means transitive. Is it antisymmetric? So one thing I should mention, if it is reflexive and transitive, we already know what kind of order it is. Which order it is? Pre-order or quasi-order, right? Pre-order or quasi-order. Oh, sorry. Or quasi-order. Okay, so if I define my specialization relation like that, this is already a pre-order or quasi-order. Is it antisymmetric? When it could be, because we already came through the separation axioms. And I talked about the opens here only, nothing else. Just try to think, don't look at your note. So for antisymmetricity, what I am demanding actually. So in whatever set X is sitting, that set Y should sit, and wherever Y sits, X should sit there. Not a T0 space means many things, you know. If it is T0, then you are telling that if it is T0, then it should be antisymmetric. Is it the case? Yes, right? So for a T0 space, my relation actually becomes antisymmetric, right? That means that relation is partial order if and only if it is a T0 space. That proof is there. I'm not going to prove it because you can get the idea like why it is so. And when it will become equality, which separation will help you to make it equal? That means that partial order becomes the equality. Can I do it with non-Hausdorff? Because I already told that that is very much important in the study of non-Hausdorff spaces, right? So is there
Purbita, do you
any-
have 2 more minutes?
Yeah,
You have 2 more minutes.
2. It's 8. 15 after
Okay, 7
18,
more
yeah,
minutes.
15,
Sorry.
yeah?
Yeah.
Okay, thank you. So that is your exercise, okay? Although I already gave the proof of that, so try to think about it. Okay, so that's it about the specialization, and I already told that many people thinks it in many different ways. Try to see that whatever I noted down and try to come up with your own ideas, like how can you call it? So I just listed some of the ideas, okay? Now I'm coming to the idea of continuity. So you know that already you have the idea that whenever you have two structures, we used to study how we can transform one from another, right? Like when we studied sets, then we studied function. When we studied order theory, I mean that partial order, we talked about that order preserving map and so on, right? In group theory, we talked about homomorphism and all. So whenever we are going to talk about some mathematical structure, wherever you will see that, we always try to think about the transformation which can preserve the structure, right? That always needed. And you will get the more ideas during your category theory courses because they will deal with lots of morphisms and you will get the general idea about it. So what is the structure kind of like in topology? What structures we do have? What will give you the idea of the structure? In some
The open
sense.
sets. The open sets.
Okay, yes. So I always have, like whenever I am talking about topology, I'm talking about a set and open sets. So somehow I need to preserve the open sets in some way. So how in the idea of continuity? So if I have two sets, say X and Y, and I have topologies over X and Y, say different topologies, of course, and a function from X to Y will said to be structure preserving or continuous. Okay, whenever I have given open sets here, say some U belongs to, or V, say V belongs to, V is open means it should belongs to tau prime. Then the inverse image of F inverse B will sitting here, some subsets of X. So what is F inverse B actually? F inverse B is the member of what? Inverse image means elements from X, some elements from X. Which type of elements? Such that F of X belongs to V. So the demand will be that wherever this inverse image of open set goes in X, it should be seated in tau. That means it's preserving the openness by its inverse image. And the inverse image is this, right? So a function from X to Y is said to be continuous function if for any opens in Y, inverse image of that will go to an open of X. That is, it is seated in the tau. Understand? I'm not writing down because it is already written there, right? So that is the idea of continuous functions. So can I ask you some of the examples? Say I am taking the set ABC and taking, say, the very normal topology, this one, phi X and A. So this is my topology, and that is my X, and that is my Y. Say I'm just taking the topology over AV and taking this only. Right? So I have A, B, C here and A here. A and B here, right? So I'm defining my mapping like that. A goes to A, B goes to B, C goes to B. Is it a mapping? It's a mapping, right? Now tell me, is it a continuous mapping? If it is continuous, I should say what? That inverse image of each open means AB, MT and A should lie inside this. Is it lying inside that? All of you are agreeing with that. Can you give me one function on that same set? कौन सा function नहीं हो गया? No, inverse image means this. You can see, na? Whatever X value is belongs to V. So what is your F inverse of my open is A, right? What is your F inverse A here? F inverse A means what? It's not inverse function. I'm talking about inverse image, right? So it is not, it shouldn't be a function, because when people are doing algebra a lot, they are confused with that. So I don't need a function in the inverse sense. It can be any relation actually. So you can understand that is a, can you give me one example with this settings that which will not be continuous? Can you assign something like ABC to AB such that it will not be a continuous? B to A. This B to A. All of you are agreeing with that? Because AB is not open in X. So that is not a continuous function. So that's the idea of the continuous function. How much time I do have? 2 minutes more. Oh my God. Okay. Just one concept I will talk about, and that's it for today. Okay. So it is also an important concept, but we need to know. It's about the compactness. Okay. So when a topological space is said to be compact, I think whoever had the idea about real analysis, they know that. So if I have a given topological space, I will say that that space is compact if every open cover of X has a finite subcover. So you encounter, whoever doesn't know about topology, they will see that I uttered two words which are not known to you, right? As a finite subcover. So we don't know what is open cover, right? And we don't know what is the finite subcover of it, right? So see that what is the open cover? An open cover are the collection of open sets, because open is there. So collection of all the open sets which can cover X, that means whose union will be your whole X. That is, X is covered by some of the elements from tau. So OIs are from tau. So if it happens, then the family of this OI will be known as the open cover of X. And X may have many open covers, right? One of them is what? Very natural. X itself, right? So that is the open cover idea. And if I count some finite number of elements from that collection of open sets, say O1, O2, .on, such that it has the ability to cover my whole space, that is I equals to 1 to n, then I'll call that this open cover has finite subcover. And if each open cover of X has a finite subcover, we will call that as the compact set, right? And what is the idea of compact set? A subset X is compact if A under its subspace topology will give you another compact space. So what is the subspace topology? Subspace topology means we are considering the topology over a subset, and topology will be what? So tau A will be the intersection of A with the members of tau, where T belongs to the original topology. And I claim that that will indeed form a topology, and that is known as the subspace topology. Okay, so you can verify it if you want to, and that if this is a compact space, then A is known as the compact set. And also I included one theorem that continuous image of compact set is compact. And another thing is there, the theorem tells that any closed subset of a compact space is compact, but I ask you whether the what can I say, the converse is true or not. If not true, give an example, so that will be taken care during your tutorial. So that's it for today.
So thanks. Thank you. So any quick questions within 2-3 minutes? Online participants? Okay, I have a question, like quickly. Yeah. I'm new to the concept of specialization. So any utility or something to that? Like, why is it introduced?
Yeah, because like some places, I'm not quite sure because I'm not expert in that field for sure. Marcus will talk about that also, because he will talk about that what are the utilization in the spectral theory. And also I already mentioned that in non-Hausdorff spaces, that space actually, that relation actually tells you that when T0 and T1 will be there, just seeing the order relation. Like when it is partial order, you can say that your space is T0. When it is equality, it is going to be T1 and so on. And there exist many other things because you can actually somehow connect your topological idea with the order algebraic structure. So that is the main idea, I guess. Like that's the answer to you. Maybe Marcus can tell you something more about it. Marcus, you want to say something?
Yeah, it's maybe beneficial to do this. So I think in the first talk there was this set of downsets of a partial order given, right?
Mm-hmm.
And this is actually a topology.
Yes.
And it would be a good exercise to check what the specialization relation of this topology is. And then you will, this is very instructive this is a process, you will actually get back the partial order of the original poset. And so in this way, this O of A from the first talk, if you hit this with this idea of specialization, you will exactly reconstruct the poset. This is very instructive, kind of. That's maybe what I can say for now. Later I will say more, of course.
I hope that you will say more in your own lecture as well.
Yes,
right?
yes.
It's more visible. Yeah. Thank you so much.
Thank you, everyone. So we'll meet again after 1 hour for the lunch break.
Yeah. Okay.
Thank you.
So we are closing the Zoom meeting. So before the next session begins, we'll reopen it.